A single deep-field image from a space telescope can expose thousands of galaxies packed into an area smaller than a grain of sand held at arm's length. Thousands inside a microscopic patch of sky. So what happens when you scale that across the entire dome of the observable universe? The answer becomes impossible to say out loud. The deeper we look, the faster the count expands, slipping out of our hands. To understand the true number, we won't guess. We'll journey through the galaxies themselves one by one until the question collapses under the weight of what the universe really contains. Before we begin the journey, one thing must be clear. Galaxies are not objects you can simply tally. The universe hides them too well. Some are drowned in dust. Some are smaller than star clusters. Many are stretched so far away by cosmic expansion that their light will never reach us, not even if we wait until the end of time. Even the best telescopes only sample thin slivers of the cosmic landscape. JWST revealed swarms of faint compact galaxies that Hubble never saw, forcing astronomers to revise the count upward again. So instead of chasing a number that keeps slipping away, we'll explore the galaxies themselves. Each one a clue, each one a piece of the universe's vast unfinished inventory. The journey begins inside a structure so vast that even light needs 100,000 years to cross it. Our galaxy is not a peaceful disk of stars. It is a rotating engine of gravity, dust and dark matter, threaded by spiral arms that drift like slow-moving weather fronts. Near the center sits a dense bar of stars, and behind it lurks a black hole 4 million times the mass of our sun. Everything we know, everything humanity has ever seen is bound to this one rotating island. And yet, compared to the galaxies waiting beyond the Milky Way, is merely a reference point, a familiar landmark before the landscape becomes strange. It gives us scale perspective, and a hint of the structures that fill the darkness beyond its edges. To understand the universe's true population of galaxies, we leave the comfort of this home spiral and push outward into a domain where the shapes grow bigger, brighter, and far less predictable. Just 2.5 million light-years from us lies a spiral, even larger, a system containing roughly 1 trillion stars. Andromeda is drifting toward the Milky Way at over 100 kilometers each second, pulled by the mutual gravity of 2 enormous halos of dark matter. Its bright core, wrapped in layers of dust and star clusters, sends a steady stream of light across the void. The galaxy is not merely an object, it is our future. In 4 billion years, its disk will merge with ours, dragging entire star systems into new orbits as the 2 spirals fold into a single swollen structure. Andromeda teaches us that galaxies are not fixed points. They collide, reshape and evolve. They trade stars, tear each other apart and build new structures from the wreckage. Counting galaxies becomes meaningless when they constantly merge into new identities. But as we pass Andromeda, the local group begins to open. Beyond it lies a sea of forms, stranger than spirals and brighter than collisions. At first glance, the Triangulum galaxy appears modest compared to its massive neighbours. It contains only a few tens of billions of stars, but its structure is unusually clean. Arms sharply defined dust lanes, delicate star-forming regions glowing in pastel colours. It is the smallest major member of our local group, yet its motion hints at a deeper story. Gravity links it loosely to Andromeda, and some simulations suggest it may have passed through Andromeda's outskirts in the distant past, triggering waves of star formation we still see. Triangulum represents something important. Galaxies are not isolated counts in a cosmic ledger. They belong to families, groups, and hierarchies. Many of them cannot exist without gravitational relationships shaping them. In the process of estimating galactic numbers, astronomers must also account for these webs of influence. Tiny galaxies that hide beside giants, streams of stars that once belonged to smaller companions, dwarf galaxies that vanish after being absorbed. The universe's census is tangled long before we leave our own cluster. Far closer to us is a smaller irregular galaxy bound tightly to the Milky Way. The Large Magellanic Cloud is not a spiral, but a distorted patch of gas dust and bright blue star clusters shaped by gravitational forces pulling it into a gentle arc. Its most iconic region is 30 Doradus, a blazing nebula that produces some of the largest known stars. Here, clouds collapse with astonishing efficiency, forming stellar giants that live fast and die violently. The LMC challenges every expectation about size. Despite being barely a fraction of the Milky Way's mass, it creates stars at a furious rate. This imbalance complicates our understanding of galactic populations. A small galaxy can outshine a large one. A faint system can host extreme phenomena, and many galaxies like the LMC are so dim they escape detection entirely from across cosmic distances. Hundreds of billions of galaxies may exist beyond our reach, simply because their starlight is too weak or too chaotic to register. The LMC is a reminder of everything the universe hides. The Large Magellanic Cloud is a galaxy caught in the middle of becoming something new. Unlike spirals or ellipticals, it has no symmetrical shape to anchor it. Instead, it looks like a torn banner drifting in the dark, its stars unevenly distributed, its gas warped into long, irregular filaments. These distortions are not random. Every wrinkle and thread is a signature left by the Milky Way's gravity. Over hundreds of millions of years, tidal forces have stretched the LMC's outer layers, tugging them into faint trails that curl into space like smoke caught in a slow wind. Even the galaxy's rotation has been altered. Rather than spinning smoothly, it twists like a cloth being wrung with regions moving at slightly different speeds. This delicate structure makes the LMC especially valuable. Because it is so close to us, astronomers can study individual stars inside it, with unprecedented detail, mapping its motions, tracing its star-forming regions and reconstructing its past encounters with our galaxy. Every measurement reveals more of the same pattern. The LMC is not a stable system, but a galaxy mid-transformation. If it were just a little farther away, its faint outer distortions would blur into the background and we would misclassify it entirely. Many distant galaxies likely suffer the same fate. Misread, misunderstood, or missed altogether because their fragile shapes dissolve into cosmic noise. Within this chaotic galaxy lies one of the most extreme environments in the local group, 30 Doradus, also known as the Tarantula Nebula. This region is a stellar nursery operating at a scale unmatched in our galactic neighborhood. Inside its bright tangled clouds are clusters of newborn stars, some exceeding 100 times the mass of the Sun. These giants burn with furious intensity, emitting torrents of radiation that carve caves and tunnels into the surrounding gas. Their stellar winds collide, forming shock fronts that trigger new waves of star formation. It is a self-amplifying cycle, creation fueling more creation, destruction clearing space for the next generation. In the center of the Tarantula Nebula lies R136, a dense cluster, housing some of the most massive stars ever observed. If such a cluster existed in the Milky Way, its light would dominate our night sky. But within the LMC, it glows from a respectful distance, a reminder of how different a small galaxy can be when conditions align. This single region produces enough ultraviolet radiation to illuminate an area hundreds of light-years wide. But the Tarantula Nebula is also a message from the early universe. Galaxies in the first billion years often behaved like this, forming stars rapidly burning through their gas and shaping their structure through violent feedback. The LMC offers us a small nearby glimpse into that ancient era. Every time we observe 30 Doradus, we are effectively peering into a cosmic time machine, seeing processes that were once common but now rare. And this leads to a crucial consequence. If galaxies like the LMC were far more common in the early universe, and if each one contained regions as bright and chaotic as the Tarantula Nebula, then our estimates of galaxy counts at high redshift may be drastically underestimated. A galaxy does not need to be large to be powerful. It does not need to be luminous to shape the universe. Many ancient galaxies may have lived fast, died young, and left behind only faint echoes too dim for our telescopes to detect unless magnified by chance. The LMC shows us that the universe is filled with surprises hiding in plain sight, waiting for us to look closely enough. The small Magellanic Cloud drifts beside the Milky Way like a fragment torn from something larger, a faint and uneven glow suspended against the dark. From a distance it looks modest, a pale smudge of scattered stars and patches of soft blue light. But as we draw closer, its true nature becomes unmistakable. This galaxy is not merely small, it is wounded. Every part of its structure bears the marks of gravitational stress, as if it has spent billions of years being pulled, stretched and reshaped by forces far greater than itself. Its stars are arranged in loose streams rather than tidy clusters. Its gas is smeared across space in irregular waves. Nothing about it is settled. This is a galaxy in the middle of being taken apart. The Milky Way's gravity is the architect of this distortion. Over countless orbits, tidal forces have torn long ribbons of hydrogen from the small Magellanic Cloud, forming the enormous structure known as the Magellanic Stream, a trail of gas extending across more than 100,000 light-years. This ribbon is so faint that most telescopes overlook it entirely, but in sensitive radio images it becomes clear. The galaxy is shedding material like a comet losing dust, each filament a signature of past encounters. Even the central regions show signs of stress. Stars move in paths that refuse to align into a stable disk. Some clusters seem to drift without belonging to any recognizable structure. The small Magellanic Cloud is not simply orbiting the Milky Way, it is being slowly dismantled by it. Yet within this chaos lies an unexpected vibrancy. Despite its distorted shape and its ongoing loss of material, the small Magellanic Cloud contains pockets of intense star formation regions, where dense clouds collapse into bright young clusters. These clusters stand out like sparks along a frayed wire. The contrast is striking. A galaxy being torn apart still finds the strength to create new stars. In this sense, the small Magellanic Cloud is a paradox. It is fragile and unstable, yet still alive with the brilliance of newborn suns. It reminds us that galaxies do not follow the simple rules of size or stability. Even the smallest and weakest among them can host dramatic energetic processes. Because the small Magellanic Cloud is so close, astronomers can examine its stars one by one, something impossible for most distant galaxies. This level of detail reveals features that complicate our understanding of galactic evolution. Many stars in the galaxy appear older than expected for such a small system, suggesting that it once had a more substantial reservoir of gas before countless interactions stripped it away. Other stars belong to streams that appear to be migrating outward, evidence that the galaxy is still losing material. Some regions appear surprisingly metal-poor, almost primitive, hinting that fresh gas from intergalactic space may be feeding into the galaxy, even as other parts are removed. This complexity makes the small Magellanic Cloud a cautionary tale for any attempt to count galaxies across the universe. If a galaxy looks this different up close, fractured, stretched, and constantly changing, how many distant galaxies are we misreading because they are too far to resolve? When we see a faint irregular glow in deep surveys, are we looking at a dying dwarf, a newborn system, or a galaxy caught in the middle of being torn apart by a larger neighbour? From far away, these distinctions blur into a single smear of light, easy to misclassify and even easier to overlook. The universe may contain billions of galaxies just like the small Magellanic Cloud, too faint, too distorted, or too intertwined with larger systems for our instruments to identify correctly. And beneath all of this lies a deeper truth. Galaxies are not static objects. They do not maintain clean shapes or predictable paths. They stretch, break, collide, merge and dissolve. They transform in ways that hide their true histories. The small Magellanic Cloud is living proof. It has survived for billions of years in the gravitational shadow of the Milky Way losing mass, with each close approach, yet still managing to produce new stars and maintain a fragile coherence. But its fate is sealed. In a few billion more years, it will likely be absorbed entirely, its stars scattered into the Milky Way's halo like grains of sand swept into a larger tide. As we drift away, the galaxy appears even smaller, even more delicate, a reminder that much of the universe is built from objects so faint and vulnerable that they barely cling to existence. Yet each one contains stories of creation and destruction of forces shaping matter across unimaginable scales. If galaxies like the small Magellanic Cloud exist in such numbers and in such fragile states, then our census of the universe is not just incomplete, it is blind to vast populations we may never fully detect. Counting galaxies is not like counting stars. It is more like counting waves in a storm shapes constantly changing, merging, fading, or being reborn from the same restless sea. NGC 1300 emerges from the darkness like a blueprint drawn with impossible precision. Even from a distance of more than 60 million light-years, the galaxy stands out among its neighbours. Its central bar stretches like a glowing spine, rigid and straight, feeding matter into a luminous inner ring. From that ring, two grand spiral arms unfurl with the symmetry that borders on unnatural. Many galaxies twist into loose wind-blown patterns, but this one behaves as though guided by invisible architecture. Every curve, every bright knot, every dark lane appears placed with intentional balance, as if the galaxy were following instructions etched into the laws of gravity. But its perfection is not the work of design, it is the work of time. NGC 1300 is the result of billions of years of rotation, collision, star formation, and gravitational negotiation. Density waves sweep through its disk like ripples across a pond, organizing gas into repeating arcs. Dust lanes carve dark filaments that split the light into thin, delicate shadows. As the bar rotates, it funnels cold gas toward the center, sustaining a slow but steady heartbeat of star formation. The innermost region, where the bar meets the ring, glows brilliantly with clusters of younger, hotter stars, evidence that the galaxy's symmetry is not static but continually refreshed by new generations of suns. The more we study galaxies like NGC 1300, the clearer it becomes that spirals are not random swirls of matter. They are long-lived patterns maintained by subtle gravitational choreography, yet the precision of NGC 1300 also exposes a limitation in our observations. Galaxies that appear chaotic may only seem so because we lack the resolution to see their internal order. At immense distances, where even JWST struggles to resolve fine structure, a galaxy as meticulously arranged as this one might look like a faint smear. We would dismiss it as irregular or unremarkable. Much of the universe may contain spirals with hidden sophistication, their beauty blurred into indistinct light by the gulf between us. NGC 1300 also offers clues about the environments where such order can thrive. It resides in a region of space that is comparatively quiet. No massive neighbours tearing at its arms, no violent mergers disrupting its shape. In this calm environment, the galaxy has maintained its symmetry for eons. Most galaxies are not so lucky. They collide, warp, and absorb smaller companions, reshaping themselves again and again. Many spirals that began as neatly structured as NGC 1300 now exist only as distorted relics of their former designs. If galaxies can lose their identity so easily, then counting them by morphological type becomes fraught with uncertainty. A galaxy observed today tells only the story of a single moment, not the countless transformations that came before. Even within its tranquil appearance, NGC 1300 hides turbulence. Deep images reveal faint streams of stars beyond the main disk. Whispers of ancient interactions hints that the galaxy may not be as isolated as it seems. These stellar streams curl around the outskirts like faint memory lines marking where dwarf galaxies were swallowed long ago. Each absorbed companion altered the galaxy's rotation ever so slightly, contributing to the spiral structure we see now. This raises an important question. How many galaxies vanish into larger systems, leaving behind nothing but trails too dim to detect? For every galaxy that survives independently, many more may have been erased in quiet mergers, never counted, never catalogued. Then there is the core. Like many barred spirals, NGC 1300 contains a compact dusty nucleus, likely housing a modest supermassive black hole. Gas spirals inward along the bar, feeding the centre at a steady rate. Sometimes the inflow strengthens, triggering brief periods of active growth. Other times it slows, leaving the core dormant. These variations create subtle differences in brightness across the galaxy variations that could mislead distant observers attempting to estimate its mass or star formation rate. A galaxy's luminosity does not always match its true scale, and NGC 1300 is a reminder that brightness alone is a poor guide to galactic census taking. As we drift farther from the galaxy, its grand structure collapses back into a single image. Two elegant arms, a bright bar, and a soft halo of scattered stars. From this distance, its perfection feels quiet, almost fragile. Yet the galaxy will continue turning its slow measured rotation long after our species is gone. It will maintain its symmetry through billions of years, a clockwork spiral marking time by the movement of countless suns. NGC 1300 stands as proof that order can emerge from chaos, that gravity can sculpt beauty from randomness, and that some galaxies hide a precision we are only just beginning to appreciate. But it also contains a warning. If a galaxy this structured can disguise its complexity behind distance and dust, then the universe may be filled with masterpieces we have never seen clearly. Galaxies whose forms remain hidden, uncounted, unknown. And if we cannot identify them, how can we ever hope to count them? NGC 1300 is not just a spiral. It is a reminder that the universe always keeps more secrets than it reveals. The Sombrero Galaxy hangs in the darkness like a luminous coin framed by a perfectly sculpted shadow, a sight so striking that even its name feels inevitable. From a distance, the galaxy appears almost unreal, a brilliant spherical bulge surrounded by a razor-thin ring of dust, the two elements locked together in dramatic contrast. No other nearby galaxy displays such bold architecture. It is as if the universe carved a monolith out of light, crowned it with a dark brim, and set it drifting across intergalactic space. The brightness of the central bulge is intense, glowing like a lantern against the void, while the dust lane cuts across it with an elegance that reveals the subtle tension between order and chaos. Up close, the sombrero's halo becomes even more fascinating. It contains an extraordinary number of ancient globular clusters, dense spherical collections of stars that orbit far beyond the main disk. Even the Milky Way, rich in such clusters, cannot compete with the sombrero's abundance. These clusters act like fossils from the early universe, each one preserving the chemistry and structure of a time when galaxies were just beginning to take shape. The sheer quantity surrounding the sombrero suggests a complex history, possibly involving the absorption of numerous dwarf galaxies whose stars were flung into the halo over billions of years. This massive population of clusters encircles the galaxy like a swarm of fireflies, faint yet persistent, each one marking a chapter of cosmic evolution we can only infer through their motion and colour. At the heart of the sombrero lies a supermassive black hole, estimated to be billions of times the mass of the Sun. Its presence explains the luminosity of the central bulge, which glows with the combined light of many densely packed stars orbiting in tight, rapid paths. Gas flows inward through the dust ring, spiralling toward the core with measured determination. Occasionally this inflow intensifies, feeding the black hole, and causing the galaxy's centre to brighten briefly, leaving faint imprints of past activity. These episodes do not transform the sombrero into a quasar, but they do hint at a restless interior hidden behind the calm exterior. The galaxy's serene appearance is the disguise of a system constantly negotiating the push and pull of gravity, radiation, and rotation. Much of the sombrero's mystique comes from its position in space. It inhabits a relatively quiet neighbourhood, not trapped inside a large cluster, not engaged in any violent mergers, and not surrounded by disruptive neighbours. This isolation allows its elegant structure to survive for billions of years without being torn or distorted, and yet hints of past interactions linger in the galaxy's faint outer regions. Subtle arcs and streaks of light barely perceptible to the naked eye reveal remnants of smaller galaxies that once passed too close, their stars now scattered across the sombrero's halo. These delicate traces act like fingerprints of ancient encounters, the only remaining evidence that this galactic monolith has not always lived in perfect peace. The dust lane, so iconic in images, is a world of its own. What looks like a simple dark line is actually a complex band of cold molecular gas and microscopic grains drifting in layered patterns. Stellar nurseries hide within it, shielded from the harsh radiation of the central bulge. Though the sombrero is not considered a starburst galaxy, the dust ring contains enough raw material to form new stars steadily over long periods. These stars illuminate the inner edges of the ring, producing a faint glow where light meets shadow. If viewed from a different angle, the galaxy might appear far less dramatic, its shape blending into the common forms of other spirals. But from the vantage, we see the dark brim cuts across the bulge with such clarity that it becomes the defining feature of the entire structure. The Sombrero Galaxy reveals a challenge in counting galaxies across the universe. Orientation and perspective can completely change our interpretation. A galaxy viewed edge-on like the Sombrero may show a sharp dust lane and a thin disk. That same galaxy viewed face-on might look like a simple bright circle with only subtle hints of its true structure. At vast distances where even JWST cannot resolve fine details, many galaxies blur into shapes that tell us little about their nature. A monolith like the Sombrero could easily be mistaken for an elliptical galaxy if seen from above its dust lane rendered invisible by the brightness of the bulge. The universe may hide countless galaxies with intricate designs behind poor viewing angles, each one slipping through our classification systems unnoticed. As we pull away, the Sombrero regains its iconic silhouette, the glowing crown, the crisp shadow, the halo of ancient clusters flickering at the edges. It remains one of the most visually compelling galaxies ever observed, reminder that the universe can produce structures as striking as any crafted by human hands. But beyond its beauty lies a deeper message. Galaxies are not simple points of light. They are complex ecosystems of matter and motion shaped by forces we can barely imagine. Many may look ordinary from afar, yet contain elaborate internal worlds that never reach our telescopes with enough clarity to be recognized. The Sombrero's dramatic form whispers something essential about the limits of our cosmic census. If a galaxy this bold can have its true nature obscured by distance angle or faintness, then what chance do we have of understanding the full population scattered across the universe? The Sombrero is both a masterpiece and a warning, an emblem of what we can see clearly, and a reminder of everything we still cannot. The Whirlpool galaxy rises before us like a cosmic hurricane frozen in time, two sweeping arms spiraling outward with a clarity so striking that it became one of the first galaxies ever classified as a true spiral. Its structure is confident and bold. Bright clusters line the arms in rhythmic intervals, each marking a burst of star formation, triggered by waves of density flowing through the disk. From afar, the galaxy looks serene, almost delicate, but the tranquility is an illusion. This is not a quiet spiral drifting through space. It is a galaxy caught in the middle of a gravitational confrontation. Clinging to the end of one spiral arm is a smaller companion. NGC 5195, a compact distorted galaxy locked in a slow but relentless orbit around the Whirlpool. The two galaxies are connected by threads of gas and dust, long tenuous bridges stripped away by tidal forces. These delicate tendrils shine faintly illuminated by clusters born from the collision of gas clouds pulled between the two systems. Each thread is a battlefield where gravity tears apart the interstellar medium, compressing some regions into knots that ignite as newborn stars while scattering others into loose curling streams. What appears like a beautiful handshake between galaxies is actually an extended struggle lasting hundreds of millions of years. The Whirlpool's perfect spiral is a direct consequence of this encounter. In isolation, spirals often drift into asymmetry, their arms fading or becoming lopsided over time. But when a smaller galaxy plunges through or near the disk, it sparks a response. Waves ripple outward from the site of the disturbance rotating with the galaxy, and shaping the gas into dense ridges that trace the arms. These arms become engines compressing clouds along their length and triggering star formation at rates far higher than the galaxy would achieve alone. This is why the Whirlpool glows so brightly an entire galaxy, operating in overdrive, forced into creative turmoil by the gravitational intrusion of its companion. Yet interactions like this are not rare. In fact, they are one of the primary drivers of galactic evolution. When counting galaxies, astronomers must consider how often systems like the Whirlpool undergo transformations that shift their brightness, shape, and classification. A galaxy caught in such a moment can appear far more luminous than usual, inflating its estimated mass. Others may appear shredded or amorphous, making them difficult to categorize. And in deep surveys of the distant universe where galaxies appear as tiny smudges, these distortions can easily be mistaken for entirely different types of objects. The cosmos does not give us static forms, it gives us phases, fleeting transitions that complicate every attempt to build a simple census. As we move closer to the Whirlpool's arms, colours and textures sharpen. Blue clusters blaze against lanes of dark dust. Redder regions mark where older stars dominate, having drifted outward from earlier epochs of star formation. Gas clouds stretch into elegant curves shaped by the rotation of the disk and by shocks from collisions between interstellar flows. In some regions, the gas is so dense that it collapses repeatedly, forming clusters layered across time-young stars, still wrapped in their natal clouds beside older, more exposed siblings. These layered clusters give the arms a beaded appearance, like glowing pearls embroidered onto a swirling tapestry. The companion galaxy NGC 5195 is far less composed. Its structure has been battered, its original shape nearly erased by repeated passes near the Whirlpool. Long streams of stars spill from its body, pulled outward like strands of silk unravelling from a fabric stretched too thin. Some of these stolen stars join the Whirlpool's halo. Others form arcs that curve between the two galaxies, tracing their mutual motion like lines etched by a cosmic artist. In simulations, interactions like these often end with the smaller companion being torn apart entirely, its remnants absorbed into the halo of the larger galaxy. The Whirlpool may be witnessing the final chapters of its partner's existence. But what makes this pair scientifically important is not just their beauty or their violence, it is what they reveal about the universe's hidden populations. When galaxies interact, they often trigger starburst regions bright enough to be seen from very far away. A distant survey might detect these glowing knots without recognizing the underlying collision. From across billions of years of cosmic expansion, the Whirlpool would appear as a bright, structured object, its companion perhaps invisible altogether. We would underestimate the complexity of the system, misjudge its age, and miscount it in our classifications. Multiply this uncertainty by billions of galaxies, and the difficulty of building a complete census becomes obvious. As we drift outward once more, the entire system resolves into its iconic shape. A grand spiral reaching toward a ragged companion, both locked in a slow gravitational dance. The Whirlpool galaxy is often used as a textbook example of a spiral, but its perfection is the result of chaos, not stability. It is a reminder that galaxies are shaped not only by their internal physics, but by their relationships with everything around them. Counting galaxies is easy, understanding their stories is not. And the Whirlpool, with its luminous arms and torn companion, shows us why the universe resists simplification at every scale. The Blackeye Galaxy appears suddenly a bright rounded core split by a single dark arc that cuts across its face like a bruise. Even in a universe filled with irregular shapes and chaotic collisions, this galaxy stands out. Its luminous centre seems almost too clean, too perfectly formed, while the band of dust slicing through it is sharp enough to look artificial. The contrast between light and shadow gives the galaxy a sense of depth, as if a scar has been burned into its surface. This one feature dominates every image, transforming an otherwise ordinary spiral into an unmistakable cosmic landmark. But the dark band is not a wound, at least not in the way it appears. It is a colossal lane of dust orbiting the galaxy's core, a dense cold structure made of microscopic grains and molecular gas. The dust absorbs light from the stars behind it, dimming their glow and creating the dramatic silhouette that defines the galaxy's appearance. If we could strip away the dust, the underlying structure would reveal a glowing, nearly spherical bulge wrapped in smooth layers of older stars. But the dust is essential to the story. It is both a shield and a shadow, an active part of the galaxy's life cycle, hiding regions of star formation and shaping the flow of gas through the central regions. The distribution of dust in the Blackeye Galaxy is unusual. In most spirals, dust spreads along the arms in long filamentary lanes that curve gracefully with the galaxy's rotation. Here the dust forms a distinct, tightly bound arc that orbits closer to the core, almost like a ring captured inside the bulge. This suggests a past encounter, perhaps a smaller galaxy once passed too close, disturbing the Blackeye's structure and causing gas to collapse inward into a compact rotating band. If this is true, then the dust lane is not simply a feature of the galaxy's evolution, but a fossil imprint of a merger long ago. The quiet surface hides a violent past. Such interactions leave behind more than visual scars. They reshape stellar orbits, generate waves of star formation, and alter the galaxy's overall rotation. In the Blackeye Galaxy, stars near the core move in slightly tilted orbits, as if following the gravitational memory of the event that brought the dust inward. Some regions contain clusters of younger stars, their blue light softened by the dust's absorption. In contrast, the outer halo contains older, redder stars that drift undisturbed. This mixture of ages and motions reveals a complex history, one that cannot be understood from a simple photograph. A galaxy may look calm, but inside it a story stretching back billions of years. The dust lane also complicates our understanding of galactic populations across the universe. Dust absorbs light, turning bright regions into shadows, and making entire galaxies appear dimmer than they truly are. At large distances, where even powerful telescopes gather only a few photons, a dusty galaxy may fade into the background. The Blackeye Galaxy is easy to recognize because it is relatively nearby, but if it were 10 or 20 times farther away, its distinctive arc might disappear. Its brightness drop below detection thresholds, and its identity as a beautifully structured spiral would vanish. Dust can hide star formation, conceal structure, and distort measurements of brightness, all factors that affect how many galaxies we think exist. The core of the Blackeye Galaxy reveals another layer of complexity. Observations show subtle variations in color and brightness, hinting at recent star formation triggered by inflowing gas. The dust lane appears to act as a reservoir, directing material toward the inner regions where it can collapse into new stars. This means the dusty scar is not simply a remnant of past events. It is actively shaping the galaxy's present. As stars form and evolve, their radiation may gradually consume some of the dust, while stellar winds push other parts outward. Over millions of years, the lane may warp, shift, or dissolve entirely. The galaxy we see today is only one frame in its long unfolding story. If we step back, the Blackeye Galaxy becomes even more intriguing. Its nearly perfect halo of old stars surrounds the brighter core like a soft vignette fading into space without abrupt edges. This halo contains clues to past mergers, with faint streams of stars stretching outward in arcs barely visible against the dark. These streams are the remains of dwarf galaxies torn apart and absorbed, ghostly reminders that galaxies survive by consuming their smaller companions. Counting galaxies becomes difficult when so many of them end their lives inside others, leaving behind only traces so faint that they often escape detection. As we drift away, the galaxy's appearance becomes simpler again, a bright orb crossed by a single dark line. But that illusion of simplicity is precisely what makes the Blackeye galaxy significant. It is a reminder that even galaxies with unmistakable signatures can hide complexity behind dust distance and time. From afar, the dust lane is all we see. Up close, it becomes a dynamic, evolving structure tied to the galaxy's deepest history. And if one galaxy can hide so much behind a single shadow, the universe may contain countless others concealing their stories behind veils of dust. The Blackeye galaxy whispers an uncomfortable truth for anyone trying to count galaxies across cosmic time. Appearances deceive. A dust lane in the wrong place can make a giant look small, or a complex system look simple. Entire populations of galaxies may remain hidden behind their own shadows, invisible to our surveys. The universe does not just hide things in darkness, it hides them in plain sight behind the shadows they cast upon themselves. NGC 253 glows like a streak of molten silver drifting through darkness. From afar, the galaxy resembles a flattened coin, heated to the edge of melting, its central regions shining with an intensity that seems to push against the night itself. But this brilliance is not the calm radiance of old stars, it is the flicker of chaos. NGC 253 is one of the nearest starburst galaxies, a system undergoing a surge of star formation so fierce that it transforms the entire structure into a furnace of light, heat, and motion. If the Milky Way produced stars at this rate, its brightness would overwhelm the entire sky. This galaxy belongs to a class of systems that operate in short, violent bursts. Gas falls inward along the disk, collecting in dense pockets near the center. These pockets collapse rapidly, forming clusters that shine with young, massive stars. Their ultraviolet radiation sculpts the surrounding gas into luminous filaments, hollow cavities, and expanding bubbles. Each new generation of massive stars lives only a brief incandescent moment before exploding as a supernova. The combined shockwaves from these explosions push gas out of the galaxy's plane, punching holes through the disk and sending plumes of material sweeping into the halo. In long exposures, these outflows look like faint red curtains billowing above and below the galactic center, slowly drifting outward as if the galaxy were exhaling fire. The most dramatic feature of NGC 253 is its core, where star formation is occurring at a rate dozens of times higher than normal. This central region is a crowded metropolis of stars packed so tightly that their light blends into a continuous glow. Massive clusters move through the heart of the galaxy like embers swirling in a forge. Dust lanes twist across the core, absorbing light and casting dark web-like shadows that break the brightness into bright streaks and dim fissures. Each of these dust lanes hides additional star formation. Within them, clusters so young that their light cannot yet pierce through the material that birthed them. But this activity comes at a cost. Starburst galaxies burn through their gas reserves with reckless speed. The gas that collapses to form stars is also needed to sustain the galaxy's long-term evolution. In NGC 253, the current starburst phase is likely temporary. Once the central gas supply runs low, the activity will fade, leaving behind an aging population of stars and a quieter disk. This cycle, periods of intense activity punctuated by long stretches of relative calm, complicates our understanding of galactic populations. A galaxy observed during a starburst may appear brighter, more massive, or more active than it truly is. Another observed before or after such a phase may seem far more ordinary. The starburst-driven winds in NGC 253 also reveal how galaxies lose mass. Gas blown out the disk may escape entirely, drifting into intergalactic space or feeding nearby structures. Over billions of years, this process can drastically change a galaxy's fate, reducing its ability to form stars in the future. In some cases, these outflows enrich surrounding space with heavy elements forged inside stars, seeding the environment for new generations of galaxies. The silver coin galaxy therefore acts as both a creator and a disperser of matter, a cosmic blacksmith hammering out stars while simultaneously scattering the raw materials of future systems. For astronomers trying to count galaxies, NGC 253 presents an important warning. Many starburst galaxies are exceptionally bright, making them easy to detect across large distances, but their luminosity is temporary. A galaxy undergoing a starburst may mimic the brightness of a much larger system, and because starburst phases are short-lived surveys of the distant universe, may disproportionately capture galaxies in these rare moments of intense activity. This creates a bias. The galaxies we see most easily may not be representative of the overall population. Some surveys may overcount bright galaxies, while others may misinterpret starbursts as indicators of higher mass or greater size. Furthermore, the silver coin's dusty disk hides significant structure from view. Dust absorbs and reddens starlight, altering the galaxy's appearance and making it difficult to measure accurately. In deep surveys, galaxies like NGC 253 might appear dimmer or more irregular than they are blending into the background noise or being mistaken for simpler dwarf systems. The interplay between dust light and star formation introduces layers of uncertainty into galactic classification and detection. Many distant galaxies caught in starburst phases may be too obscured to observe clearly, while others may shine so brightly that they obscure nearby objects. As we drift away from NGC 253, the galaxy's chaos becomes unified again. A silver blaze wrapped in swirling bands of dust drifting quietly against the black. Its starburst phase will not last long in cosmic time, but in this moment it stands as one of the brightest beacons in its region of space. It represents the dual nature of galaxies, capable of periods of extraordinary creativity yet also vulnerable to the exhaustion of their own resources, and it highlights a fundamental challenge in our quest to count galaxies. The universe is full of systems caught in transition, their properties shifting on timescales that complicate every measurement. The silver coin galaxy is not merely a starburst galaxy. It is a reminder that galaxies live complex dynamic lives that cannot be captured in a single observation or a single number. If entire phases of galactic evolution can transform their brightness, structure, and detectability, then our cosmic census is incomplete by design. An NGC 253 blazing fiercely in the darkness stands as proof that the universe is far more transient, far more dynamic, and far more unpredictable than any tally can capture. IC 1101 looms out of the dark like a continent made of stars, a structure so vast that it stretches the limits of what a galaxy can be. At more than 5 million light-years across, it dwarfs even the largest spirals in the nearby universe. With a Milky Way placed inside it, our entire galaxy would sink into the central region, like a pebble dropped into an ocean. IC 1101 is not a spiral, nor a barred system, nor a delicate disk. It is an enormous elliptical galaxy, an ancient swollen sphere with a soft, diffuse glow that extends so far from the core that its edges blur into intergalactic space. From afar, the entire object resembles a bright ember surrounded by a cloud of ghostly light. This sheer size is not a coincidence. IC 1101 sits at the heart of a massive galaxy cluster, a gravitational metropolis where hundreds of galaxies drift, collide, and merge over billions of years. In such environments, small galaxies rarely survive intact. They spiral inward, torn apart by tidal forces long before reaching the center. Their stars are absorbed into the halos of the giants, while their gas is stripped and dispersed into the intracluster medium. Over cosmic time, one central galaxy grows fat on the remnants of countless others. IC 1101 is the product of this endless consumption, a galaxy built not from a single collapse of gas, but from the cannibalized remains of many generations of smaller companions. Despite its immense mass, the galaxy's light is strangely gentle. Its stars scatter outward in a smooth gradient lacking the sharp structures we associate with spirals. There are no arms, no bars, no dust lanes, only the dim glow of ancient stellar populations that have aged together for billions of years. The lack of structure is a clue to its history. Spirals and other organized forms cannot survive the repeated mergers that IC 1101 has endured. Each collision disrupts the ordered rotation of stars, stirring them into random motions until the galaxy becomes spherical and featureless. In such a system, stars follow their own individual paths, moving in orbits that crisscross unpredictably, rather than participating in a single, rotational dance. The core of IC 1101 is even more extreme. Observations suggest the presence of a supermassive black hole so enormous that its mass may be several billion times that of the Sun. This colossal object sits at the gravitational center of the galaxy, anchoring the chaotic orbits of the stars around it. Gas drifting toward the core may heat up and emit radiation, though much of the surrounding material has long since been consumed or expelled. In many giant ellipticals, the central black hole undergoes periodic bursts of activity, blasting jets of energetic particles into space. If IC 1101 has experienced such episodes, they have likely shaped the surrounding cluster, heating the intergalactic gas and suppressing new star formation on scales that dwarf the galaxy itself. This environment creates complications for anyone trying to count galaxies in the universe. Clusters like the one surrounding IC 1101 are so crowded that individual galaxies blend into one another, especially as smaller systems dissolve into streams too faint to detect. A distant observer might mistake the entire cluster for a single complex object. Conversely, they might underestimate the brightness of the central galaxy if its outer halo fades into the background noise. Light from the giant can also overwhelm nearby dwarfs, causing them to disappear entirely from surveys. In deep images, faint galaxies can only be detected if their light stands out above the glare of brighter neighbours, a requirement that eliminates countless systems in dense regions. The halo of IC 1101 extends so far that it interacts directly with the intracluster light, a diffuse glow composed of stars stripped from galaxies during past collisions. This faint background fills the space between galaxies, masking the borders of individual systems and complicating efforts to identify where one galaxy ends and another begins. Counting galaxies in such an environment becomes a matter of interpretation rather than direct measurement. What qualifies as a separate galaxy? A tight cluster of stars, a faint shredded arc of light, a barely visible patch of diffuse glow. Different surveys answer these questions differently, leading to variations in galactic census results that grow larger with distance. IC 1101's existence also raises another question. How many similar giants lie beyond our observational reach? Massive ellipticals like this one form primarily in the densest regions of the universe, many of which lie far beyond the current limits of our telescopes. At extreme distances, even the brightest giants become faint smudges. Their halos disappear entirely, their true mass hidden behind the diminishing brightness imposed by cosmic expansion. If we cannot see these colossal structures clearly in our own cosmic neighborhood, how many more remain undetected across the billions of light years that separate us from the edge of the observable universe? As we drift away, the full scope of IC 1101 becomes impossible to ignore. Its diffuse halo stretches outward like a fading memory of countless galaxies long since devoured. Its core burns with the compressed history of everything it has absorbed. Its presence in the cluster shapes the motions of its neighbours, bending the fabric of space with its immense gravitational weight. And all of this is just one galaxy, one example among billions of systems shaped by forces we have only begun to understand. IC 1101 teaches us that even the largest, brightest galaxies hide more than they reveal. It reminds us that the universe is filled with giants cloaked in faint light, their true nature invisible from afar. And if a galaxy this vast can escape clear detection at greater distances, the cosmic census becomes far more uncertain than we once believed. Counting galaxies is not simply a matter of observing what is bright enough to see. It requires understanding what lies beneath the glow, the history's collisions and erased galaxies that built these giants from the ashes of countless smaller worlds. Hercules appears unassuming at first glance, a modest elliptical galaxy resting quietly in a distant cluster. Its light is smooth, pale, and old, radiating the calm glow typical of environments where star formation slowed billions of years ago. To the eye alone, nothing about this system suggests violence, but the illusion shatters the moment we switch from visible light to radio wavelength. Suddenly the galaxy erupts across the sky like a detonating sun. Two enormous jets blaze outward from its core, each one stretching far beyond the boundaries of the galaxy itself. These jets are not thin streams. They are titanic plumes of plasma swollen into vast lobes by their collision with surrounding gas. In radio images, the system becomes one of the brightest objects ever observed. These jets originate from a supermassive black hole at the center of the galaxy, a monster hundreds of millions of times the mass of the Sun. As matter spirals inward toward its accretion disk, magnetic fields twist and accelerate charged particles to near-light speeds. These particles blast outward along the poles, carving tunnels through intergalactic space. Over millions of years, the jets inflate into two balloon-like structures, each larger than the galaxy that birthed them. If we could see radio light with our eyes, this entire region of the universe would glow like a burning forge with Hercules A at the heart of the fire. Such structures are not merely dramatic, they carry enormous influence. The expanding lobes heat the surrounding gas, preventing it from cooling and collapsing into new stars. This feedback regulates the galaxy's growth, ensuring that it does not become a runaway behemoth. Yet the process works on scales so vast that the jets can reshape the entire cluster environment. They create cavities in the intergalactic medium that stretch hundreds of thousands of light years, altering the motion of nearby galaxies and changing the temperature of gas far from the core. The galaxy's calm appearance in visible light hides a central engine powerful enough to sculpt the landscape of space itself. This contrast, a quiet glow overlaying a raging interior, reveals the biases in our observations. Galaxies that look dormant in one wavelength can roar with intensity in another. If we rely only on optical data, we miss an entire population of radio-dominant systems. Some may appear faint or unremarkable in visible light, causing them to slip through detection thresholds. Others may blend into the background, overshadowed by brighter optical galaxies. Hercules A teaches us that the universe's complexity cannot be captured by a single type of telescope. Counting galaxies requires a multi-frequency approach, or we risk missing entire categories of cosmic behavior. The shape of the jets themselves tells a story about the environment. Their curved edges and turbulent interiors reveal that the galaxy is plowing through a medium dense enough to push back. The intergalactic gas heated by previous generations of jets now acts as both fuel and resistance. As the lobes expand, they sweep up this gas, compressing it into thin shells that glow faintly in radio light. In some regions, this compression triggers new pockets of star formation as the pressure forces clouds to collapse. In others, the jets tear through the material so violently that star formation is halted entirely. This dual nature, both destructive and creative, makes radio galaxies key players in the evolution of clusters. At the core, chaos reigns. The accretion disk around the black hole flickers with bursts of energy, its brightness changing as fresh matter spirals inward. Gas clouds funnel toward the center, along ill-defined paths, their motions disturbed by the gravitational agitation caused by past mergers. The black hole itself may have grown through a series of collisions with the nuclei of smaller galaxies. Each merger would have sent ripples through the stellar population, heating the orbits and contributing to the smooth spheroidal structure we see today. The central region holds the accumulated memory of all those past events, light-bent matter, consumed stars scattered. Because of these internal processes, Hercules A helps illuminate a hidden truth about the cosmic census. Galaxies are often defined more by their activity than their appearance. A system that seems quiet may be among the most powerful engines in the universe. Without radio telescopes, we might classify Hercules A as a mundane elliptical galaxy, just another pale sphere floating in a distant cluster. Yet in radio light, it becomes a titan, a system whose influence stretches over millions of light years. How many galaxies across the cosmos hide similar engines unseen because their jets are oriented away from our line of sight, or because their radio lobes have faded into the background? How many have we missed entirely? As we retreat into the darkness, the galaxy resolves into its deceptive calm once more. A soft glow, an ancient halo, a shape untroubled by visible structure. But we now know better. Beneath that tranquility lies a force capable of reshaping its environment on scales few galaxies can match. Hercules A is a reminder that the universe hides its extremes behind ordinary masks, that a single galaxy can become a furnace bright enough to carve cavities into space, and it warns us that any attempt to count galaxies must contend not only with distance and faintness, but with a hidden violence that transforms these systems in ways our eyes alone cannot see. Hoag's object floats in the darkness like an optical illusion suspended in space. A perfect ring of brilliant blue stars encircling a golden sphere of older light. Nothing bridges the gap between them. No faint spiral arms, no wisps of connecting dust. Just emptiness, clear and precise, as though the universe carved a hole between two galaxies and stitched them together into a single impossible shape. At first glance, it resembles a portal more than a system of stars, a glowing circle, framing a core far too smooth to belong to the same structure. Even seasoned astronomers describe it as unsettling, because galaxies almost never obey such symmetry. The outer ring is composed of young, massive stars, hot blue, and arranged in a band so cleanly defined that it could be mistaken for architectural design. These stars formed from gas compressed into a circular wave, a phenomenon theorized but rarely seen with such clarity. The interior core, by contrast, is an older, rounder, metal-poor population glowing with the warm luminosity of suns that have burned quietly for billions of years. The two components appear to ignore each other, entirely orbiting around a shared center, yet separated by a gap that contains almost no stars at all. This void reinforces the illusion that the ring and core are separate galaxies accidentally aligned, even though they are gravitationally bound. The most accepted explanation for this cosmic geometry begins with an ancient collision. Long ago, a smaller galaxy may have plunged directly through the center of the golden core, creating a shock wave that rippled outward like a stone dropped into a pond. That ripple compressed the surrounding gas into a circular front-igniting star formation along its expanding edge. Over time, the wave moved outward, leaving behind a bright blue ring. Meanwhile, the intruding galaxy was likely shredded by tidal forces, its stars either absorbed into the core or flung into intergalactic space. If this model is correct, the ring is not a static structure, but the fossil of an event that transformed the galaxy in a matter of millions of years. Yet Hoag's object is not fully explained by this scenario. The symmetry is too clean, too exact, and too well preserved. Other collisional ring galaxies, such as the Cartwheel Galaxy, show distortions, knots of intense star formation and asymmetric waves, but Hoag's object looks almost mathematically perfect. Its ring shows no significant breaks. Its course sits precisely at the center. The stellar populations on both sides follow rotation curves that seem delicately balanced. This suggests a more stable long-term evolution, one that preserved the shape rather than letting it decay into irregular chaos. Some researchers propose that this system may have formed through a resonance mechanism rather than a collision with gravitational patterns, reorganizing the gas into circular structures without violent impacts. If so, it represents one of the purest examples of galactic self-organization ever discovered. What makes Hoag's object invaluable to our understanding of the universe is not just its beauty but what it tells us about the limits of detection. From moderate distances, a ring galaxy appears as a faint halo. The empty gap becomes invisible. The core and ring blur into a single smudge. Only the nearest examples reveal their true nature. If Hoag's object were 10 times farther away, it would simply register as an odd elliptical. If it were 20 times farther, it might not be recognized as a galaxy at all. This sensitivity to distance means that the universe may contain countless ring systems, each one intricate, each one born of unique circumstances that remain hidden behind the blurring effects of cosmic expansion. The core also conceals clues about the galaxy's past. Spectroscopic studies show hints of stars with slightly differing chemical signatures, suggesting that not all were born in the same environment. Some may have originated in the smaller companion that collided with the system long ago. Others may have formed later as the galaxy stabilized. These subtle differences would be invisible in deep surveys of distant space, where only broad colors and rough shapes can be measured. A galaxy like this, if seen at great distance, would be misclassified, miscounted, or simply overlooked. It reveals how fragile our cosmic census is when so much information is lost to darkness. Another mystery lies beyond the ring. Deep images show faint stars far outside the main structure. Tiny clusters that may be remnants of tidal streams or the last echoes of past mergers. These features are so subtle that many telescopes miss them entirely. They demonstrate that Hoag's object is not isolated. It carries the fingerprints of its interactions, the faint scars of cosmic encounters that shaped its current form. Yet these details contribute to its deceptive elegance, making it appear more pristine than it truly is. As we drift farther away, the galaxy returns to its iconic silhouette. The radiant ring, the glowing core, the dark empty space between. The image is mesmerizing, an impossible circle suspended in star-studded silence. Hoag's object is one of the most visually striking galaxies ever observed, but it's not merely an artistic curiosity. It is a reminder that the universe is capable of producing structures far more diverse than expected. Rings, arcs, layered populations, hollow centers. These forms complicate every attempt to categorize the cosmos. And if such rare geometries exist so close to us, how many more lie beyond our reach, unresolved by even our best instruments? Hoag's object teaches us humility. It shows that even a single galaxy can defy our expectations, hiding complexity inside a perfect circle. It warns us that distance can erase details essential to understanding cosmic evolution. And it invites us to consider that the universe's diversity is not an exception. It is the rule. A ring this flawless is not simply a cosmic spectacle. It is a quiet challenge to our belief that we can ever truly count the galaxies scattered across the night. Dragonfly 44 is one of the most unsettling galaxies ever discovered, not because of its appearance, but because of its near absence. From a distance, it looks like a faint smear of light, barely brighter than the background sky. Its stars are so sparsely distributed that large regions contain more darkness than starlight. If one were to pass it in the night sky without knowing what to look for, it would vanish entirely. Yet this ghost-like structure holds a secret so extraordinary that it challenges our assumptions about how galaxies are built. The visible stars within this system amount to only a tiny fraction of what its gravity demands. When astronomers measured the motions of those few scattered suns, they discovered something astonishing. The galaxy behaves as though it has the mass of the Milky Way, hundreds of billions of solar masses, yet it contains only a whisper of starlight. The only explanation that fits is dark matter. Not just some dark matter, but a staggering amount of it. In this dim system, dark matter dominates almost completely. The stars are merely decorative, the faintest shimmer on the surface of an enormous invisible structure. This discovery transforms the galaxy from a faint curiosity into a revelation. It demonstrates that not all galaxies shine, and not all mass announces itself with light. If a system this dark can masquerade as an inconspicuous patch of sky, how many more exist? How many enormous halos of dark matter wander the universe with only a handful of stars clinging to them, too faint for our telescopes to register? The existence of such an object suggests that the population of galaxies we can see may be only a fraction of what truly exists. The universe may be filled with dark galaxies, systems with enormous mass but almost no light hidden in the shadows between brighter neighbours. The internal dynamics of this shadow giant deepen the mystery. Its stars move faster than expected for a dim low-mass dwarf. These high velocities reveal the immense gravitational pull of the dark matter halo, yet the few stars present do not form a disk or any recognisable shape. They drift in vaguely spherical distributions as if sprinkled randomly across a void. There are no spiral arms, no dust lanes, no bright knots of formation. Star formation appears to have stalled long ago, leaving behind only the aging remnants of a population that never grew large enough to illuminate its surroundings. It is a galaxy stripped down to its skeleton, an exposed framework of gravity, without the luminous flesh typically associated with galaxies. The origin of such a system remains unclear. Perhaps it began as a normal dwarf galaxy whose gas was stripped away early in its life by the harsh winds of a nearby cluster. Without gas, it could not form new stars, and the few it possessed gradually aged into the dim lights we see today. Or perhaps it formed as a dark matter-dominated halo that never accumulated enough gas to ignite significant star formation. Another possibility is even more intriguing. This ghost galaxy might be the remnant of a once larger system, its luminous components torn away by tidal forces, leaving behind only the gravitational core. Whatever the explanation, the existence of such an extreme structure broadens our understanding of what a galaxy can be. Observationally, this system exposes one of the greatest challenges in the cosmic census. Faintness does not equal insignificance. Traditional surveys rely on light on the assumption that galaxies announce themselves through brightness, but the dark matter empire demonstrates that some of the universe's most massive structures hide between the thresholds of detection. If something this large and this massive can be nearly invisible, then our telescopes are blind to entire categories of galaxies. Even when we detect them, measuring their true nature is difficult. Faint galaxies provide few stars to trace their motion, making mass estimates uncertain and classifications ambiguous. We are left with only partial glimpses of structures that hold enormous importance in understanding cosmic evolution. The surrounding environment complicates the story further. Dragonfly 44 resides within a dense cluster where gravitational interactions are frequent. In such environments, smaller galaxies are often stripped of their gas and stars, leaving behind faint diffuse remnants floating through a harsh landscape. This harsh treatment can transform once bright dwarfs into ghostly structures nearly indistinguishable from dark halos. It is possible that this system represents one phase in a long sequence of erosion, a victim of the cluster's gravitational tides. If so, then clusters across the universe may be littered with similar husks, each housing a massive halo of dark matter, but emitting barely any light. Even its discovery reveals how fragile our understanding is. It was detected not through brightness, but through deep, long-exposure surveys designed specifically to catch ultra-diffuse galaxies, objects so faint that standard surveys would have overlooked them entirely. Without the specialized instruments and careful methods used by the Dragonfly telephoto array, this galaxy would still be hiding in plain sight. And that raises an unsettling question. How many dark behemoths remain unseen simply because our tools are not tuned to notice them? As we drift away from this ghost of a galaxy, it fades almost immediately, dissolving into the background like a shadow returning to darkness. Its presence is easy to forget, yet its implications are impossible to ignore. It forces us to confront the reality that the universe is not built from light alone. Vast structures may exist without shining. Mass may hide behind invisibility. And the galaxies we see, glorious spirals, blazing starbursts, elegant rings, may represent only the bright minority. Dragonfly 44 is a quiet reminder that what we observe is not the full story. It is a whisper from the dark side of the cosmos telling us that the universe is deeper, stranger, and far more populated than the glowing shapes we can count. And if giants like this can hide in the faintest corner of the sky, then our cosmic census, no matter how advanced, will always be incomplete. They appear first as small round dots, barely noticeable, almost playful in shape. When volunteers in a citizen science project first stumbled upon them, their bright green glow stood out sharply against the usual reds and blues of galaxy surveys. These compact spheres looked nothing like the elegant spirals or massive ellipticals that dominate astronomical images. Each one was a tiny bright bead with a colour so unusual that the volunteers nicknamed them peas. What they had actually found was far more significant. A population of galaxies that act like time machines, offering a glimpse into the conditions of the early universe. These miniature galaxies, only a few thousand light years wide, burn with astonishing intensity. Their green colour is not from stars themselves, but from the intense emission of doubly ionized oxygen, a signature of incredibly energetic environments. Inside each of these spheres, massive young stars blaze at temperatures so high that they flood the surrounding gas with ultraviolet radiation. This radiation strips electrons from atoms, causing the gas to glow with a distinctive hue. The result is a compact, luminous knot in which star formation is happening so fiercely that the galaxy feels less like a settled system and more like a spark thrown from a cosmic forge. Though small, these firecrackers behave like scaled-down versions of the galaxies that existed when the universe was only a few % of its current age. Back then, gas was more pristine, low in heavy elements, and galaxies had not yet stabilized into grand spirals or smooth ellipticals. They were chaotic, compact, and intensely productive. The peas echo that ancient era. Their low metallicity suggests that their gas has been little enriched by previous generations of stars. Their star formation rates are astonishing for their size, creating clusters so bright that they dominate the entire system. If one of these galaxies existed near the Milky Way, it would appear as a glaring emerald blaze in the night sky. The internal structure of these compact bursts reveals the complexity hidden inside their simple shapes. Turbulent clouds collide and fragment, forming high-density pockets that collapse into massive stars. Radiation from these stars pushes back against the surrounding gas, sculpting it into irregular cavities and shock fronts. Supernova explosions occur frequently, each one injecting energy into the system and triggering more star formation. In some regions, the gas becomes so ionized that it allows ultraviolet photons to escape directly into intergalactic space. This property, called Lyman continuum leakage, makes the peas important analogues for understanding how the early universe became reionized. They may be among the few nearby systems that behave like the first galaxies capable of lighting up the cosmos. But these tiny spheres also highlight a major challenge in counting galaxies. Their compactness and brightness make them easier to detect than many larger but fainter systems. A survey optimized for finding luminous points may pick up firecrackers like these, while missing vast populations of dim dwarfs. Conversely, at great distances, peas blur together with foreground noise, or appear as indistinct smudges, making them difficult to classify. Their unusual colors help them stand out in specific surveys, but at higher redshifts, the color shifts into wavelengths that require infrared instruments. Without the right tools, these galaxies become invisible, even though they might represent a significant fraction of star-forming systems in certain epochs. The discovery of these compact bursts also raises a deeper concern. If such energetic galaxies exist in the nearby universe, albeit rarely, how many more existed in the distant past when conditions favoured their formation? The early cosmos might have been filled with analogues of these green spheres, small, chaotic, rapidly evolving galaxies that lived fast and died young. Many of them burned through their gas and faded into faint dwarf systems long before their light could reach us. Others merged into larger galaxies, their individuality erased. Still others may lie at such extreme distances that even the James Webb Space Telescope can capture only the faintest hints of their glow. In this sense, the Ps are windows not just into our cosmic past, but into the limitations of our observations. They demonstrate that a galaxy's importance is not tied to its size. Some of the smallest systems can be among the most influential, especially in shaping the early universe. Their compact starbursts drive winds that push gas outward, enriching intergalactic space with the heavy elements needed for future generations of stars and planets. Their intense radiation helps ionize the early cosmos. Their rapid evolution compresses billions of years of galactic development into a much shorter timescale, yet many remain too faint to detect beyond relatively modest distances. As we drift back from one of these cosmic firecrackers, the bright green glow fades into a tiny bead, then into a point, and finally into nothing at all. These galaxies can disappear from view with the slightest increase in distance, reminding us how fragile our cosmic census truly is. If entire populations of energetic, rapidly evolving systems vanish with distance, or blur into indistinguishable specks, then our understanding of galactic demographics becomes skewed by the simple fact of what is easiest to see. The Ps whisper a quiet warning. The universe is full of extremes that our surveys may not capture. Small galaxies can burn brighter than giants. Faint systems can hold the keys to ancient epochs, and some of the most important actors in cosmic history may be the ones we overlook because they do not fit our expectations. The green spheres discovered by volunteers are not oddities. They are signposts pointing toward a universe far richer, more diverse and more dynamic than the luminous spirals and enormous ellipticals that dominate our imagination. Some galaxies burn with a kind of desperation, as if racing against a cosmic clock only they can hear. These are the starburst galaxies that form stars at rates so extreme that they reshape themselves in the process. From afar, they may look like ordinary spirals or dwarfs, but the moment we peer into their cores, the truth becomes unmistakable. Gas clouds collapse so quickly and so violently that the interior glows with a fierce blue-white blaze. Clusters of massive stars ignite almost simultaneously, flooding their surroundings with ultraviolet radiation. What should take hundreds of millions of years occurs in a fraction of that time. These galaxies behave like cosmic furnaces pushed far beyond their intended limits. In these overclocked systems, gas is both the engine and the fuel. Large reservoirs of cold hydrogen are funneled inward by tidal forces bars or past interactions. When enough of it accumulates, gravity triggers a runaway collapse. A single region can birth thousands of stars, many of them massive enough to burn themselves out in only a few million years. These stars radiate intensely, heating nearby gas to temperatures that create turbulent eddies and shock fronts. Supernova explosions follow shortly after each one, sending shockwaves that compress additional gas and trigger the next generation of star formation. It is a self-sustaining cycle of ignition and destruction, a chain reaction that spreads through the galaxy like fire travelling through dry underbrush. The result is a galaxy glowing with overwhelming intensity. In optical wavelengths, these systems can appear deceptively beautiful. Bright knots scattered along spiral arms, glittering clusters lining the disk, incandescent cores, burning like miniature quasars. But beneath the glow lies a chaotic battle between gravity pressure and radiation. Winds from massive stars and supernovae blow out vast cavities, punching holes in the disk that vent hot gas into the halo. These outflows form towering plumes visible in infrared and X-ray observations. In some galaxies, the winds become so powerful that they carry away more gas than the system can afford to lose, effectively shutting down future star formation. What begins as a moment of intense creativity ends with the galaxy starving itself into long-term quiet. Because these starbursts evolve so rapidly, they complicate our attempts to understand the universe's population of galaxies. Observed at the height of their activity, they appear brighter, more massive, and more energetic than they truly are. But this phase is short-lived, lasting only a few tens of millions of years. so surveys may capture them only in rare fleeting moments. A galaxy seen in full blaze may be misinterpreted as a massive giant in the making. The same system observed just before or after the burst may appear faint, small, and unremarkable. This temporal bias creates an uneven census of galaxies, especially in deep surveys where individual systems are represented by single snapshots, frozen across billions of years of cosmic expansion. Dust adds another layer of complexity. Starbursts are often shrouded in thick clouds of gas and dust, the very material that fuels their rapid formation cycles. This dust absorbs visible light and re-radiates it in the infrared, hiding the true scale of star formation from optical surveys. Some of the brightest star-forming galaxies in the universe, so-called infrared luminous systems, are almost invisible in visible light. Without the right instruments, they would blend into the background undetected. The early universe likely contained countless dusty starbursts, whose brilliance in the infrared was muted by cosmic distance. Counting galaxies in that era requires far more than optical images. It demands a broad view across wavelengths to reveal the systems that hide behind their own creation. These runaway factories also reveal something profound about how galaxies grow. Many of the massive ellipticals seen today likely passed through one or more starburst phases in their youth, consuming gas rapidly before merging with others to form vast quiescent giants. In other cases, interactions between galaxies trigger bursts that drastically alter their evolution. Two spirals passing near each other can ignite simultaneous starbursts, doubling or tripling their brightness. A smaller companion plunging through a disk can concentrate gas into rings or waves that collapse into clusters. Even minor interactions can produce dramatic results, and because starbursts shine so brightly they can be seen across enormous distances, acting as beacons, marking the sites of collisions and transformations that would otherwise remain hidden. Yet the most important lesson these systems offer is philosophical as much as scientific. They demonstrate that galaxies do not evolve smoothly. They do not follow neat timelines or predictable growth patterns. Instead, they lurch through chaotic episodes, burning through their resources in sudden explosive fits. Some may flare only once before settling into a quiet adulthood. Others may undergo multiple cycles, each one reshaping their structure and altering the trajectory of their future. When we observe distant galaxies at high redshift, we often see them during these luminous fits of activity simply because those are the moments when they shine brightly enough to become visible. The calm, mature phases remain hidden by distance and time. As we pull back, a starburst galaxy transforms again. What once looked like a furnace of blue fire becomes a more ordinary structure. Dusty arms, bright knots, a glowing core. With each step farther, details blur and the violence diminishes. Eventually, the entire galaxy becomes a single bright point in a field of countless others. Its internal fury disappears behind the veil of distance. And in that transition lies the challenge. If we cannot see the chaos within, how can we hope to understand the true demographics of the cosmos? These overclocked galaxies remind us that brightness does not always reveal size, that faintness does not always imply insignificance, and that the universe's most dramatic events often occur in systems too small or too distant to capture fully. They are cosmic forges that burn fiercely for brief moments before fading into quiet. And if so much can happen in such a short span of time, then our attempt to count galaxies based on narrow windows of observation captures only a sliver of what truly exists. They should not exist, at least not in the form we find them. Imagine a galaxy as large as the Milky Way, stretching tens of thousands of light years across, yet containing only a whisper of starlight. The space between its stars is so vast that entire solar systems could drift for ages without encountering another. These are the ultra-diffuse giants, vast puffed-up worlds that look like unfinished sketches of galaxies, as if someone traced the outline but forgot to colour in the details. At first glance, they appear as faint smudges in deep surveys so dim that early astronomers dismissed many of them as imaging artifacts or distant clouds of gas. Only when long exposures and careful processing highlighted the breadth of these structures did their scope become clear. They are enormous, true galactic-scale objects, but with the surface brightness of a dying ember. In some cases, the brightness is so low that a smartphone camera aimed at the night sky might record something just as luminous. And yet, despite their transparency, these ghostly giants are held together by gravitational forces far stronger than their limited light suggests. The explanation lies in their invisible backbone. Many of these systems appear to be dominated almost entirely by dark matter. Their stars drift through enormous halos that outweigh the visible material by factors of hundreds or even thousands. This invisible scaffolding allows them to grow to sizes rivaling major galaxies, even though they lack the luminous populations that make typical spirals so brilliant. Their motions tell the story. Stars within these faint monoliths move faster than expected for such thinly populated systems, tracing out the gravitational presence of vast amounts of unseen mass. Without that dark framework, the galaxies would fly apart like scattered dust. And yet not all of these dim colossi follow the same rules. Some appear strangely deficient in dark matter, almost as if they were stripped bare by tidal forces. They drift in clusters surrounded by galaxies massive enough to tear at their outer layers. Over billions of years, interactions with their neighbours may have puffed them up, scattering their stars outward, until the systems became ethereal shells of their former selves. These fragile remnants challenge the idea that dark matter is always dominant. They suggest stories of violence, galaxies pulled apart, stretched thin and left as ghostly silhouettes. Their shapes reflect this turmoil. Unlike spirals or ellipticals, these galaxies often lack clear structure. Some are oval clouds, others are nearly spherical. A few hint at faint arms or central condensations, but even these features appear fragile and blurred. Dust, if present at all, is minimal. Gas is often depleted, leaving behind only aging stars. These characteristics paint a picture of systems that have lived hard lives, buffeted by their environments, stripped of their resources and left to drift like cosmic relics. The environment plays a defining role in their fate. Many of these dim giants reside in dense clusters where gravitational tides are relentless. Nearby galaxies carve them apart, and the cluster's hot, turbulent gas strips away what little material remains. In such hostile environments, even a modest burst of star formation becomes impossible. The galaxies fade further, becoming so dim that even powerful surveys struggle to detect them. Many more likely remain hidden entirely, blending into the background noise of deep images like faint shadows lost in a sea of brighter structures. This raises a critical issue for our cosmic census. How many galaxies do we simply fail to see? If enormous structures can hover just above the threshold of detectability so faint that only specialized instruments like the Dragonfly Array can reveal them, then countless more may be lurking unseen across the universe. Traditional telescopes focus on bright, concentrated sources of light. They excel at finding spirals, starbursts, and compact dwarfs, but the faint diffuse giants slip through the gaps. Their light spreads across too much sky to trigger detection algorithms, or it fades into noise before it can be confirmed. Even when detected, these systems challenge classification. Are they failed spirals, stripped dwarfs, or unique galaxies that formed in unusual conditions? Their diversity suggests that multiple formation pathways exist. Some may have once been normal galaxies whose gas was removed early. Others may have formed from unusually turbulent patches of matter, expanding into diffuse forms as they matured. Some might even be progenitors of future mergers, vast airy structures waiting to be absorbed by larger neighbours. The uncertainty surrounding their origins and their numbers complicates our understanding of the universe's structure. If these faint monoliths are common, then the true number of galaxies may be far higher than current estimates. They add invisible weight to clusters, influence gravitational lensing signals, and alter the way mass is distributed across cosmic filaments. Yet they barely shine. Their existence serves as a quiet reminder that the universe is not built solely from things we can easily see. As we drift away, one of these dim giants loses coherence quickly. Its stars blur into the background. Its outline dissolves. A few steps farther, and the entire galaxy becomes indistinguishable from the faint glow of intergalactic space. It is not gone, only hidden. And therein lies the challenge. If an object the size of the Milky Way can vanish into the darkness, how many more galaxies hide in the vast expanses beyond our reach? These invisible giants remind us that light is not the full story. The universe contains structures held together by gravity alone, their stars too few to announce themselves across cosmic distances. They whisper from the edge of detection, telling us that the cosmos is deeper, softer, and far more elusive than the bright spirals and blazing cores that dominate our images. Counting galaxies requires more than a tally of what glows. It requires an awareness of what fades, what hides, and what refuses to shine at all. At first glance, this galaxy seems almost ordinary, an elliptical glow with a faint haze around its outskirts. But then the light bends into a subtle arc and another, like ripples spreading outward from a stone dropped into still water. The galaxy reveals a set of enormous loops extending far beyond the bright core. These arcs are intricate, layered, and ghostly, curving with a precision that feels deliberate. They are not spiral arms. They are not collision debris flung randomly into space. They are imprint signatures slashed into the galaxy by an ancient event whose echoes still shape its form. In deep exposures, the ripples sharpen. Some arcs are bright, glowing with the light of stars that moved together in synchronized motion long ago. Others are faint and wispy, stretched nearly to transparency by gravitational tides. Together, these loops resemble the wake patterns behind a boat slicing through water, except they were carved not in seconds, but across hundreds of millions of years. The galaxy's smooth central glow stands in stark contrast to these outer waves, making the structure look like a cosmic brow raised in quiet surprise. Hence its evocative nickname among astronomers, the cosmic eyebrow. These ripples likely emerge from a dramatic encounter in the galaxy's past. Long ago, a smaller companion may have plunged into its outer halo, disturbing the gravitational balance and launching oscillations through the stellar population. The intruder's path created a shock wave that pushed stars into new orbits, forming the concentric arcs we see today. The magnitude of the disturbance suggests that the encounter was both close and violent, an event powerful enough to reorganize tens of billions of stars, while still delicate enough to preserve the overall shape of the larger galaxy. The resulting rings are not random. They align along a preferred axis, tracing the trajectory of the vanished intruder. In some interpretations, this system resembles a collisional ring galaxy, but with far more subtlety and complexity. Unlike the dramatic bullseye structure of the Cartwheel Galaxy, this ripple-etched giant displays layers of waves, each one slightly offset from the last. This indicates that the disturbance was not a single event, but a sequence of oscillations like a bell continuing to vibrate long after it has been struck. The arcs provide a rare look at the dynamic interior of a galaxy, revealing how stars behave like fluid under the influence of gravity. They show that galactic structures are not static sculptures, but living systems responding to every encounter and perturbation. These loops also reveal the limitations of our cosmic census. When seen from large distances, the arcs fade into invisibility. Even strong telescopes struggle to detect structures this faint. A galaxy like this might appear perfectly ordinary in low-resolution surveys and elliptical with no distinctive features. Only deep high-contrast imaging exposes the fossil waves etched into its outskirts. At greater distances, these waves would be lost entirely, meaning that many galaxies with similarly rich histories may appear deceptively simple. The universe may be filled with systems bearing these scars, yet too distant or faint to show their true complexity. The arcs help us reconstruct the galaxy's orbital history. Stars pushed outward by the disturbance now follow elongated paths that take them far from the core before looping back inward. Each orbit contributes to the shape of the ripple, stretching and compressing, the stellar population like the vibrations of a plucked string. The age of the arcs can be estimated from their spacing. Older ripples lie farther from the core, having had more time to expand outward. This layered structure provides a timeline of the galaxy's past interactions, a kind of cosmic seismograph, recording the tremors of gravitational encounters long finished. But if these ripples are the result of a merger, where is the intruding galaxy now? It may have been completely absorbed, its stars dispersed into the halo, and its gas consumed by the central regions, or it may still be drifting nearby as a faint dwarf, its brightness too low to stand out against the complex foreground. Either way, its influence persists in the arcs it left behind. This is the nature of galactic evolution. Encounters are forgotten by the galaxies involved, but their signatures endure in the structure of stars. The cosmic eyebrow highlights a hidden truth about galaxy classification. Many systems that appear calm or featureless are actually mosaics of fossil waves, distorted halos and collision remnants. At the limits of our vision, these details blur away. A distant galaxy may appear smooth, not because it is simple, but because the traces of its past are too faint to see. This challenges the notion that ellipticals are quiet, uneventful remnants. In reality, many have undergone repeated interactions that reshape their outer halos into faint arcs, shells, and loops. As we pull away, the ripple pattern softens into the galaxy's overall glow. The arcs become indistinguishable from the halo, blending into the gentle gradient of starlight surrounding the core. Viewed from even a modest distance, the loops disappear entirely. The system looks like a featureless ellipse, quiet, ancient, predictable. But we now know better. Beneath its calm surface lies a history of upheaval, written in ripples large enough to span tens of thousands of light years. And those waves remind us that galaxies often hide their deepest stories in their faintest structures. This ripple-carved giant tells us something essential about the universe. Complexity fades with distance. Details that define a galaxy's true identity can vanish in the noise, leaving behind only vague impressions. Counting galaxies becomes not just a matter of identifying light, but of recognizing that much of a galaxy's life, its collisions, its transformations, its scars can be erased simply because our observations are too shallow or too far away. They hang in space like two living creatures frozen mid-embrace, their elongated tidal tails stretching outward like slender arms. These arcs, shaped like delicate antennae, give the merging pair their famous nickname. Seen from afar, the two galaxies appear intertwined in a slow-motion collision, a dance choreographed by gravity alone. But behind the apparent elegance lies a storm of unimaginable violence. Stars are being hurled from their orbits. Clouds of gas are crashing together. Tidal forces stretch entire structures into thin ribbons that span tens of thousands of light years. In these colliding spirals, beauty and destruction unfold together. At the moment captured by our telescopes, the two disks have already passed through each other once. Their collision triggered shock waves that rippled across their interiors, compressing gas into dense knots. These knots ignited with brilliant star formation, creating clusters so massive and so luminous that they rival the brightest regions of the Milky Way. In infrared and X-ray observations, these clusters glow like embers inside a furnace. The collision has transformed these galaxies from quiet spirals into starburst engines, each core feeding a frenzy of stellar birth. The heart of the system is a turbulent maelstrom. Gas clouds swirl chaotically, forming bridges between the two shrinking galaxies. Some clouds collapse into new stars. Others are shredded by tidal forces before they can ignite. Streams of matter flow inward toward each galactic nucleus, fueling central starbursts and thickening the black hole accretion disks that lurk deep inside. The central regions are so crowded with newborn stars that radiation pressure carves bubbles into the surrounding gas. Supernova explosions erupt frequently, each one injecting energy into the chaotic environment and contributing to the perpetual storm. Despite the violence, the collision follows a predictable sequence. When two spirals meet, their interplay of gravity produces the long tidal tails that give the system its iconic form. These tails are not random debris. They are stars pulled from the outer arms of the galaxies, flung outward along precise gravitational pathways. Their shape records the angle and speed of the encounter like a fingerprint. The arcs curve gently across space, their tips fading into wisps so faint that deep exposures are required to reveal them. Each tail contains clusters of stars and pockets of gas that may eventually form dwarf galaxies, tiny offspring born from the gravitational chaos. The true complexity of this merging pair becomes clear when we consider its future. Over the next few 100 million years, the two galaxies will spiral closer, their orbits decaying as gravitational tides rob them of angular momentum. With each pass, the cores will grow more distorted, the gas more turbulent. Eventually, the two nuclei will coalesce into a single massive center. The result will not be a spiral at all, but a giant elliptical galaxy, smooth, featureless, and governed largely by random stellar motions rather than organized rotation. This is the fate of many spirals in crowded cosmic environments. They are destined to merge, smoothing their structures into larger, more diffuse shapes. Because merging systems are so chaotic, they complicate attempts to count galaxies in the universe. Depending on the stage of the collision, a system like this may be classified as one galaxy. Two galaxies or several objects connected by tidal debris. Some surveys treat each nucleus as a separate system. Others classify the entire structure as a single entity. At great distances, the tidal tails become invisible, and the two bright cores may appear as separate points of light. Conversely, if the two cores blend in low-resolution images, they may seem like one elongated galaxy. The ambiguity grows with distance. Beyond a few billion light-years, the entire collision could be reduced to a faint blur indistinguishable from the background. This classification confusion contributes directly to uncertainty in the cosmic census. Collisions are not rare events, they shaped the growth of most galaxies we see today. Throughout the universe, countless pairs, triplets and groups undergo similar interactions at various stages. Each one evolves rapidly compared to cosmic timescales, shifting categories as they merge. A single system may be counted differently depending on the wavelength survey depth and resolution used. Thus, collisions act not only as engines of galactic transformation, but also as sources of observational confusion, blurring the boundaries between what qualifies as one galaxy and what qualifies as several. The twin arcs of the antennae also demonstrate how galaxies shed mass during encounters. Stars flung into intergalactic space form extended halos and tails that persist long after the cores merge. These structures are extremely faint and easily missed by surveys. As a result, the true mass and history of merging galaxies often remain hidden behind the limits of detection. Only deep, high-contrast imaging reveals the delicate filaments that complete the full picture. Without such observations, our understanding of how galaxies grow becomes incomplete. The most dramatic transformations remain partially invisible. As we drift away from this celestial collision, the intricate details fade. The shock fronts blur. The bright clusters soften into pale glimmers. The tidal tails, once sharp arcs across the sky, dissolve into faint threads, barely distinguishable from the background. Eventually, the entire structure reduces to two glowing cores, suspended in a haze, mere points of light that betray nothing of the violence within. From a little farther still, even those bright points merge into a single smudge. The collision disappears behind the curtain of distance, and what remains is simply another faint galaxy in a crowded universe. This merging pair reminds us that galaxies are not static islands of stars. They are evolving entities constantly reshaped by encounters and collisions. Their forms are temporary, their boundaries fluid, their identities shifting with time. And because so many systems undergo these transformations, the task of counting galaxies becomes inseparable from understanding how they merge. The antennae teach us that a galaxy's brilliance today may hide the remnants of many past lives, and that behind the light we see lies a turbulent history shaped by gravity's relentless hand. It stretches across the darkness like a cosmic comet, an elongated stream of stars trailing behind a compact glowing head. The tadpole galaxy has one of the most dramatic shapes in the nearby universe, a form that looks more like a celestial fish or a luminous arrow than anything resembling a traditional spiral. The long stellar tail extends for nearly 300,000 light-years, far longer than the galaxy's main body. It is a river of scattered suns, bright clusters, and reassembled debris pulled outward in a single gravitational tide. This shape is not the product of internal evolution, but the frozen aftermath of a near catastrophe. Long ago, this system passed dangerously close to another galaxy, too close to escape unscathed, yet not close enough to merge. The interaction created a tension between their gravitational fields, stretching the smaller system into a distorted form. Stars in the outer regions were tugged outward, forming the extended arc that now trails behind. Gas clouds stripped from the spiral disk collapsed into bright clusters that dot the tail like beads on a string. Some clusters are so luminous that they rival the brightest nebulae in the Milky Way. They are stellar nurseries born from violence, their existence tied entirely to the collision that reshaped the galaxy. The central body remains compact but bears scars of the encounter. Its spiral arms are warped and asymmetric, twisted into uneven patterns that differ from the classic orderly spirals seen in calmer galaxies. Dust lanes weave across the core, evidence of recent star formation, triggered by gas funneled inward during the near collision. The core is a hybrid part survivor part, newly forged structure reshaped by gravitational tides yet still recognizable as a spiral. This dual personality makes the system an ideal laboratory for studying how galaxies respond to external disturbances. The long tail offers insight into how stellar material behaves under extreme stress. Stars follow ballistic trajectories determined by the gravitational tug-of-war between the two galaxies during their closest approach. The most loosely bound stars were flung farthest away, creating the extended tail. Meanwhile, gas clouds were compressed by shock waves induced by the encounter, forming clusters of massive young stars. These clusters glow intensely, providing bright markers that trace the tail's structure and motion. They are living fossils of the collision, each one a snapshot of the moment gravity sculpted the galaxy into its unusual form. The physics of such tidal features complicates the effort to count galaxies in the universe. At moderate distances, the tail becomes nearly invisible, fading into the background like a barely perceptible smudge. The bright clusters might be detected individually, but without the context of the tail, they could be mistaken for separate dwarf galaxies. In low-resolution surveys, the elongated shape blends with the sky, making the entire system look like a faint, distorted ellipse. Only deep exposures reveal the true extent of the tidal structure. At greater distances, the tail would vanish entirely and the galaxy would be classified incorrectly, either as a compact spiral or as a faint irregular. This uncertainty adds noise to the cosmic census. Interactions like this are more common than they appear. In the early universe, when galaxies were smaller and more densely packed, encounters were frequent. Many ancient systems likely experienced similar tidal stretches, though their tails would have faded over billions of years. Stars originally pulled outward may now orbit in extended halos, or have migrated to larger structures after subsequent mergers. The tadpole galaxy is a rare moment captured mid-transformation, a system frozen in a stage that most galaxies experienced, but few retain today. Its existence suggests that many galactic structures we observe in the early universe may be transitional forms rather than stable types. The tail also highlights a deeper challenge. The universe is filled with structures that are too faint, too diffuse, or too temporary to capture, unless telescopes observe with extreme sensitivity. Galaxies with prominent tidal debris may appear entirely normal if viewed from the wrong angle or at insufficient depth. Their histories vanish in the noise of cosmic distance, leaving behind only incomplete clues. When astronomers count galaxies or categorize them based on morphology, these faint features can lead to misclassification. A system with an enormous tail may be counted as one galaxy, two, or many, depending on the resolution and wavelength used. As we move farther from the tadpole galaxy, the vibrant clusters in the tail blend together, then fade into a thin line, then into nothing. The core itself shrinks to a tiny knot of light. Eventually, from a sufficiently distant vantage point, the entire system looks like a single dim smudge, its dramatic transformation erased by the sheer scale of the cosmos. This gradual disappearance reveals how fragile details are in the context of galaxy surveys. The closer we are, the more complexity we see. The farther we drift, the more the universe simplifies itself, hiding its spectacular distortions behind the blur of distance. This stretched wanderer teaches us that galaxies are dynamic, flexible structures, formed and reshaped by interactions across cosmic time. A single near collision can transform a spiral into a comet-like shape, create star clusters in tidal streams, and alter the internal dynamics of the core. Yet from far away, all this complexity is invisible. When we attempt to count galaxies across the universe, we are ultimately counting simplified silhouettes, not the full histories, scars, and transformations etched into their stars. Seen from afar, this galaxy resembles a wide-brimmed hat floating in the cosmic dark, a glowing central bulge wrapped by a razor-thin disk of dust. The silhouette is unmistakable. The bright central sphere rises like a golden dome while the edge-on disk cuts across it with perfect sharpness, creating a contrast so striking that the galaxy looks like a crafted sculpture rather than a natural structure. Its symmetry is uncanny, its proportions exact, and its presence in the night sky feels almost artificial. No wonder astronomers nicknamed it the sombrero, a galaxy that wears its identity proudly luminous and serene. The central bulge or crown is unusually bright. It contains a dense concentration of ancient stars, hundreds of billions of them packed into a region far smaller than the Milky Way's inner core. Their combined glow produces a sphere of golden light that seems to radiate warmth across the disk. Buried deep within this bright heart lies a supermassive black hole, estimated to be more massive than 1 billion suns. Though largely quiet today, its enormous gravity has shaped the bulge over billions of years, influencing the orbits of stars and the behavior of gas swirling toward the center. If the black hole were more active, the galaxy might blaze like a quasar. Instead, it rests, allowing the majestic structure around it to take center stage. The disk, by contrast, is dark, an elegant ribbon of dust and gas that outlines the galaxy's true shape. When viewed edge-on, it appears as razor-thin lines slicing across the bulge, but in reality it contains lanes of material that feed star formation. Embedded within the dust are pockets of cooler gas forming nurseries where new stars ignite. Some regions glow faintly in infrared light, hinting at a steady ongoing creation of stellar populations. Unlike many spirals, however, this galaxy's disk lacks dramatic arms. Instead, it forms a smooth, tightly wound structure with little asymmetry, as if the entire system were spun from a single motion and preserved in near-perfect stability. The hat brim extends outward, far beyond the bright core, forming a halo of scattered stars and globular clusters. These clusters, ancient, densely packed spheres of stars, surround the galaxy in large numbers, more than in many similarly sized systems. Their distribution suggests a long history of mergers and accretion events. Over billions of years, smaller galaxies may have been consumed, their globular clusters incorporated into the halo like jewels set along a crown. Each cluster is a relic from the early universe, preserving stars older than most structures in the galaxy itself. Their presence hints at a complex past hidden behind the outward simplicity of the sombrero's design. Yet the most fascinating aspect of this luminous crown is the way it illuminates the limitations of our observations. From the right angle, the disk's thinness becomes exaggerated, making the galaxy appear far smaller than it truly is. At greater distances, the halo fades into darkness, and the bulge becomes the dominant feature, causing the galaxy to resemble an elliptical rather than a spiral. Even the dust lanes, so striking in detailed images, can vanish entirely in low-resolution surveys. Without sufficient depth, the entire system could be misclassified, its intricate mix of disk bulge and halo reduced to a single glowing dot. This variability demonstrates how orientation and distance distort our perception of galactic structure. The sombrero also complicates the cosmic census, because its qualities blur the lines between categories. It possesses a massive bulge typical of ellipticals, but a rotational disk typical of spirals. Some astronomers classify it as a spiral, others as a lenticular, and still others as a transitional form. Its exact nature depends on the wavelength used to observe it and the level of resolution available. At high redshift, where galaxies appear as tiny smudges, systems like this would defy easy categorization. They could inflate the number of spirals or conversely swell the ranks of ellipticals depending on survey biases. One galaxy becomes many possibilities. Its shape also reveals clues about how galaxies grow in isolation. Unlike merging systems whose structures are torn apart by tidal forces, this galaxy's form is remarkably undisturbed. The dark dust lane remains crisp. The bulge remains round and symmetrical. The halo shows no large tidal streams or shells. This suggests that the galaxy has not undergone a major merger in billions of years. Instead, it has evolved slowly, accreting smaller companions but avoiding catastrophic encounters. This longevity enables the dust lane to retain its form and the bulge to shine steadily, creating the elegant silhouette we recognize today. Yet even in its quiet state, the galaxy is not static. Cold gas continues to descend along the disk, forming new generations of stars. The bulge slowly brightens as older stars evolve. The halo widens as faint clusters migrate outward. Every part of the galaxy is in gentle motion, a testament to the subtle but persistent forces shaping its evolution. And viewed from just a slightly different angle, many of these details vanish, leaving behind a much simpler impression than the one our telescopes reveal. As we drift away, the galaxy shrinks rapidly. The disk thins into a hairline streak. The bulge compresses into a single sharp point. Eventually, from a sufficiently distant vantage point, the sombrero becomes indistinguishable from thousands of other faint dots scattered across the sky. Its iconic shape, its dust lane, its luminous core, everything that makes it distinctive disappears behind distance and loss of resolution. This elegant hat-shaped system teaches us an essential truth. Galaxies are multi-layered structures, and their identities can shift depending on how they are observed. Classification is subjective, shaped by wavelength, depth, and viewing angle. And because the universe is vast, most galaxies, no matter how unique, fade into anonymity as soon as they are too far away. When we attempt to count galaxies across the cosmos, we are not counting structures in their full richness. We are counting impressions, silhouettes, hints of detail blurred by time and distance. Some galaxies seem almost too perfect, as if sketched by a patient artist tracing arcs across the cosmos. The Pinwheel Galaxy is one of those rare creations, an enormous open-faced spiral whose arms unwind in sweeping curves that stretch tens of thousands of light-years from the core. Its structure is delicate, yet immense, symmetrical, yet full of subtle irregularities that reveal the internal forces shaping it. From the moment we see it, the galaxy feels familiar in a way few others do. It embodies the classic idea of what a spiral galaxy should be, a celestial pinwheel turning in the dark. Its central nucleus glows with the warm light of older stars, forming a calm, concentrated heart. Surrounding it, the spiral arms radiate outward like currents of starlight, each arm filled with clusters, dust lanes, and regions of star formation. These arms are not rigid structures. They are density waves patterns moving through the disk that compress gas as they pass, triggering the birth of new stars. In some regions, the arms appear feathered, splitting into smaller filaments that twist and recombine. These fine structures record the choreography of gravity rotation and interstellar turbulence. Dust lanes lace through the arms in intricate patterns. Their dark threads provide contrast that highlights the galaxy's geometry. Within these lanes lie clouds of cold gas, the raw material for future stars. Ultraviolet images reveal the hot blue light of recently formed clusters scattered along the arms like glowing beads on a spiral thread. Infrared images show warm dust heated by newborn stars. Radio observations outline reservoirs of hydrogen waiting to collapse. Across every wavelength, the galaxy reveals another layer of its complex multi-generational life cycle. One of the most striking features of this sprawling spiral is its scale. Its diameter extends far beyond many typical spirals, giving it a sense of openness, as though its arms are stretching to fill as much space as possible. Yet despite its size, the arms maintain remarkable clarity. They do not blur into a chaotic mess. Instead, they retain structure across immense distances, showing how gravitational harmony can persist, even in a system with billions of stars. The balance required to maintain such stability is extraordinary. Too much turbulence and the arms would break apart. Too little, and the spiral pattern would collapse inward. This elegance makes the pinwheel an important reference point for astronomers studying spiral structure. It demonstrates how density waves shape star formation, how interactions with nearby companions can trigger subtle asymmetries, and how feedback from massive stars influences the surrounding interstellar medium. Close examination reveals small distortions, tiny warps, shifts in the winding of certain arms, asymmetries in brightness. These are hints of past gravitational nudges from neighbouring galaxies. Even the most perfect spirals are not immune to the influences of their cosmic environments, but this perfection also hides challenges for our attempt to count galaxies in the universe. A system like this is easy to classify when observed up close with high resolution, but from far away its defining features begin to disappear. The arms blur into the disk, the dust lanes lose contrast, the core becomes a single bright dot surrounded by a faint halo. At even greater distances, the entire galaxy may appear as a soft elliptical glow, its spiral identity erased by the limits of resolution. This effect plays a major role in high redshift surveys, where many spirals likely masquerade as featureless blobs simply because the sharpness of their arms cannot survive cosmic distance. Orientation adds another layer of complexity. When seen face-on, the galaxy reveals its full beauty, but tip it slightly and the spiral pattern becomes less distinct. Tilt it further and the arms overlap, dust lanes obscure starlight and the structure loses clarity. Observed edge on this majestic spiral becomes a thin streak across the sky, difficult to distinguish from lenticular galaxies or even disks without arms. Modern surveys rely on algorithms to classify morphology, but even those struggle when structure is partially hidden. This means that countless spirals across the universe may be misclassified, introduced into the cosmic census, under categories that do not reflect their true nature. The pinwheel also reminds us that galactic beauty is a product of time. Spirals do not form instantly. They emerge from a delicate interplay of rotation, density, and feedback. This process requires billions of years, ages long enough for stars to be born, evolve, and die, enriching the surrounding gas so that new generations can form. In the early universe, many galaxies were too chaotic or too compact to develop such extended spirals. Only after cosmic time smoothed out turbulent motions did grand designs like this become common. Thus, galaxies like the pinwheel are milestones, markers of maturity and cosmic evolution. As we drift away, the galaxy's intricate details dissolve, the star-forming knots blur, the dust lanes fade, the arms contract into soft curved traces of light. Eventually, the entire structure reduces to a single shining disk indistinguishable from countless others. Its perfect spirals, so clear up close, vanish into the smoothness imposed by distance. And in that transition lies a critical insight. What we perceive as a simple galaxy at great distance may up close be a masterpiece of structure. This luminous whirlpool teaches us that galaxies are far more complex than their distant silhouettes imply. They are dynamic mosaics of stars, gas, and dust shaped by time and interactions. They carry hidden distortions, subtle asymmetries, and long histories encoded in every filament. When we attempt to count galaxies by what we see from afar, we're really counting simplified projections of much richer structures. And for every perfect spiral like this, countless others hide their elegance behind the blur of distance, waiting for closer eyes to reveal the true artistry of the universe. Seen through optical light, this galaxy appears as a long glowing bar, an elongated ember stretched across the sky. But switch to infrared or X-ray and the view transforms entirely. What seemed calm becomes a storm. A reddish glow bursts from its center, rising in towering plumes that stream outward from the core. These plumes are not dust lanes or spiral arms. They are wind's massive galactic outflows driven by one of the most intense star-forming engines in the nearby universe. This is why the system earned its fiery nickname, the Cigar Galaxy, a place where stars ignite with such feverish intensity that the galaxy appears to exhale flame. At the core of this elongated furnace lies a sprawling starburst region, dense with clusters of massive hot stars. These newborn giants burn through their fuel in only a few million years, bathing their surroundings in ultraviolet radiation. Their wind's powerful streams of charged particles push dust and gas outward, forming a turbulent cavity. But the true chaos comes from the supernovae that detonate soon after. Each explosion unleashes more energy than the sun will radiate in its entire lifetime. The combined effect of thousands of these overlapping blasts drives a continuous outflow, pushing matter upward and downward along the galaxy's minor axis. These outflows glow brightly in infrared and X-ray, revealing the extreme temperatures and shock fronts inside the winds. The galaxy's elongated shape amplifies this effect. Instead of a wide spiral disk that disperses material evenly, the narrow, cigar-like form channels gas inward toward the central starburst. This funneling accelerates the collapse of gas clouds, making the star formation rate dramatically higher than in typical disks. As gas continues to pile into the center, the starburst feeds on itself, sustaining the winds that blast outward like jets from an engine. Observed in real time, the core behaves almost like a continuous detonation, a region where new stars ignite as fast as old ones die. But the winds do more than create visual spectacle. They shape the long-term evolution of the galaxy. As the outflows sweep gas out of the central region, they remove the very material needed to continue forming stars. This sets an upper limit on how long the starburst can last. Eventually, the galaxy will exhaust its fuel and the star formation rate will collapse. What remains will be a more quiescent system, still elongated but far less luminous, cooling, in the absence of the intense energy that drives its winds today. In this sense, the Cigar Galaxy is a snapshot of a transient phase, a galaxy living at a pace it cannot maintain. The winds also enrich the space around the galaxy. As they carry dust and metals outward, they contribute to the halo of hot gas that surrounds the system. This halo contains the heavy elements forged inside earlier generations of stars, now cast outward by the starburst's explosive force. Over cosmic time, the halo may cool and condense, forming new stars far from the central region. Or the material may drift away entirely, joining the intergalactic medium and seeding distant regions with the elements required for planets and life. The galaxy's starburst does not only transform its own structure, it influences the chemical landscape of the larger cosmic neighborhood. For astronomers attempting to count galaxies, this elongated starburst poses another subtle problem. Depending on the wavelength observed, it may appear as entirely different objects. In optical light, the system looks like a narrow bar, perhaps a small spiral or an irregular galaxy. In infrared surveys, the bright outflows dominate, making it appear larger and more energetic. In X-ray, the system becomes almost unrecognizable, with plumes extending far beyond the visible disk. Each wavelength emphasizes different structures, and surveys that rely heavily on a single band may classify the system inconsistently. From a great distance, the distinction becomes even more ambiguous. Distance also erases detail. Seen from billions of light-years away, the outflows would fade first, leaving only the core's bright starburst visible. The elongated shape might blur into a rounder profile, causing the galaxy to resemble a small elliptical. In some surveys, the intense luminosity of the central region might cause the system to be counted as a compact starburst, while in others the faint extensions might go unnoticed entirely. A single galaxy could easily be misclassified as multiple small objects if the central clusters appear as separate points in low resolution. The Cigar galaxy warns us that galaxies are not uniform across wavelengths or across epochs. A starburst today may fade into obscurity tomorrow. A system that appears small in optical light may be vast in infrared. A galaxy driven by extreme star formation may look like a faint smudge once the burst ends. When we survey the universe at different distances and wavelengths, we're not seeing consistent structures. We're seeing moments, slices of evolution that shift depending on when and how we observe them. As we drift away from this elongated giant, the fiery plumes shrink, dissolving into soft glows. The core dims into a compact streak of light. Eventually, the entire galaxy becomes a thin, faint line in the darkness, a shape so simple that its true nature is concealed. Up close, it is a turbulent machine, a place where stars roar into existence and blast gas into space. From far away, it is almost nothing at all. This contrast reveals a broader truth. Galaxies live complex, fast-changing lives, yet our cosmic census captures only thin snapshots of that complexity. Systems like this show how easily structure, activity, and identity can be lost to distance. When we attempt to count galaxies across the universe, we must remember that what we see depends entirely on when and how we look, and that behind every faint smudge may lie a furnace burning with unimaginable power. They drift near the edge of our night sky like pale, detached fragments of a larger world, two luminous patches suspended in darkness. To the unaided eye, they resemble scraps of torn nebulae floating far beyond the Milky Way's spiral arms. But these drifting satellites are not clouds at all. They are galaxies, dwarf companions moving in restless orbits around our own, bound to us by gravity, yet forever tugged and stretched by our massive halo. The Magellanic Clouds are among the closest galaxies we can see, making them windows into galactic evolution at an intimacy rarely granted by cosmic distance. The larger companion, glowing softly with a mottled mix of bright knots and dusty patches, shows all the features of a small but vibrant spiral. It lacks the tidy shape of well-formed disks, instead displaying an asymmetrical, disrupted structure. Its bar is off-center. Its spiral arms are uneven. Stars cluster in chaotic pockets as if the galaxy is still trying to assemble itself from scattered material. This disarray is not a flaw. It is a symptom of its dynamic relationship with both the Milky Way and its smaller sibling. Tidal forces sculpt its form, pulling at its arms, stirring its gas and triggering bursts of star formation. The smaller companion is even more irregular. It looks like a broken shard of a galaxy, a glowing crescent with wisps trailing outward. This irregularity is a sign of constant motion. The galaxy is being stretched by gravitational tides and buffeted by the Milky Way's halo of dark matter. Gas is stripped and reshaped into elongated filaments. Stars cluster in bright pockets where turbulence compresses the gas just enough to ignite new regions of star formation. Despite its modest size, the dwarf is a place of intense activity, its structure continuously rewritten by external influences. Together, the tidal twins leave behind a long stream of gas known as the Magellanic Stream, a vast ribbon that stretches across the sky for more than 500,000 light-years. This stream is a direct record of the gravitational struggle between the Milky Way and its companions. Gas torn from the dwarfs flows behind them like a trailing wake, weaving through the halo in complex patterns. Embedded within the stream are small clumps dense enough to form stars, suggesting that dwarf galaxies do not merely lose material, they redistribute it across vast regions, enriching the surrounding environment with fresh ingredients for new generations of stars. The close proximity of these companions allows astronomers to study their structures in detail impossible for distant systems. We can resolve individual stars, map gas flows, measure proper motions, and track how tidal forces warp their shapes. This level of resolution reveals that even small galaxies have complex internal dynamics. Their star-forming regions vary in metallicity. Their gas clouds move along irregular orbits. Their structures change over tens of millions of years rapidly by cosmic standards. They resemble living organisms more than static objects always responding to the gravitational pulls around them. Their presence also challenges the idea that galaxies evolve in isolation. Even the Milky Way is shaped by its companions. As the dwarfs orbit, their gravity tugs on our outer halo, creating ripples that propagate through the disk. Some models suggest that past interactions with these drifting satellites may have triggered waves of star formation in the Milky Way's outer regions. The gas transferred from the dwarfs may eventually mix with our own contributing material that will one day form new stars and planets. Galactic evolution is not a solitary process, it is a dance, and even giants like the Milky Way must move to the rhythms set by smaller partners. But proximity also reveals the limits of our cosmic census. If these dwarfs were twice as far away, they would appear drastically different. Their irregular shapes would blur, their star-forming knots would fade, the long gas stream would become invisible, lost in the background. They might be classified as faint irregulars or even overlooked entirely. At 10 times their distance, they would shrink to faint smudges, easily mistaken for background noise. Many galaxies across the universe exist at such marginal brightness that they evade detection simply because they sit too far away. If two dwarf galaxies this large and this close can nearly disappear behind cosmic distance, what chance do smaller or more diffuse galaxies have of being counted at all? Even their identities raise questions about classification. Are they separate galaxies? A binary system? A pre-merger pair? Their motions suggest that they may have once been gravitationally bound to each other before falling into the Milky Way's influence. If so, they represent a transitional form, a pair of dwarfs caught in the act of becoming something new. Counting them as two independent galaxies oversimplifies their true nature. Counting them as one ignores their distinct histories. Across the cosmos, similar systems, pairs, triplets, and clusters of dwarfs blur the definition of what constitutes a single galaxy. As we drift away, the glowing patches soften into pale smears. The irregular shapes vanish. The gas stream dissolves into the darkness. Eventually, the two galaxies merge into the background of the Milky Way's halo, appearing as faint, irregular clouds barely distinguishable from nebulae. What was once a pair of richly detailed companions becomes almost nothing at all. And this disappearance underscores a profound truth. Distance erases identity. The farther a galaxy lies, the more its unique character fades into abstraction. These restless companions remind us that even the nearest galaxies challenge our ability to categorize and count them. They show that proximity reveals complexity, that structure is fleeting, and that galaxies, even small ones, are molded by interactions with their neighbors. When we attempt to tally the galaxies across the universe, we rely not on perfect knowledge, but on glimpses distorted by distance, resolution, and perspective. And if the nearest examples already push the limits of clarity, then the distant universe must be far more crowded, varied, and difficult to measure than we can ever fully grasp. It is one thing to miss distant galaxies at the edge of the observable universe. It is another to overlook a galaxy practically touching our own. Yet for decades, astronomers did exactly that. The Canis Major over density. Our closest known galactic neighbour remained hidden in plain sight, buried behind the Milky Way's thick disk, concealed by dust clouds and overlapping star fields. Not until the early 21st century did detailed surveys reveal the truth. This strange imbalance of stars in that direction was not a quirk of the Milky Way, but the remains of a small galaxy being slowly torn apart and absorbed into our halo. The discovery was startling. Here was a dwarf galaxy so close that its stars intermixed with our own, yet it had evaded detection simply because our line of sight crossed dense regions of dust and gas. The hidden dwarf stretches across the sky like a faint smear intersecting the galactic plane. Its stars are older, redder, and arranged in a shape distinct from the surrounding disk populations. When mapped in 3 dimensions, they trace a structure that wraps around the Milky Way like a dissolving ribbon, evidence of a long ongoing merger. This galaxy is not just near us, it is inside the process of becoming us. This buried companion has already lost much of its original mass. The immense gravity of the Milky Way pulls at it, constantly stretching it into a distorted shape. Stars are stripped away and drawn into elongated tidal streams that wrap around the disk. Some of these streams have been detected looping high above the plane, forming diffuse arcs of stellar debris. These arcs reveal the orbit of the dwarf and the timeline of its disintegration. Over billions of years, the Milky Way has swallowed this small galaxy, piece by piece absorbing its stars into our halo, while the core continues to erode. The dwarf's proximity allows astronomers to study the mechanics of galactic cannibalism at an unprecedented scale. We can track individual stars, measure their velocities, and determine their chemical signatures. Many of these stars show lower metallicity than typical Milky Way populations, confirming their extragalactic origin. Some carry distinctive abundance patterns, unique fingerprints that identify them as immigrants captured from the beneath-the-disk intruder. By mapping these patterns across the sky, astronomers reconstruct the history of the merger, revealing how dwarf galaxies contribute to the growth of larger spirals. The discovery also illuminated a remarkable structure known as the Monoceros Ring, a vast, faint overdensity of stars encircling the Milky Way's outer disk. For years, astronomers debated whether this ring was part of our galaxy or the remains of another. The Canis Major companion provided an answer. Many of the stars in the ring share the same chemical and orbital characteristics as the hidden dwarf's debris. This suggests that the ring is not a native feature of the Milky Way at all, but a ripple sculpted by the merging dwarf, an arc of debris caught in mid-accretion. This realization reshaped our understanding of galaxy formation. It showed that even large spirals like the Milky Way grow not through smooth, steady processes, but through a series of mergers with smaller systems. Each dwarf contributes stars, gas, and dark matter. Some leave quiet signatures, subtle ripples in the halo or streams that mix gradually. Others, like this buried companion, leave more dramatic imprints. Stellar rings, warped disk regions, disrupted orbits. The Milky Way is not a pristine spiral evolving in isolation. It's a mosaic built from the remnants of galaxies long since consumed. Yet the most striking lesson from this discovery is how easily a galaxy can hide even when it's practically touching ours. The proximity of the Canis Major overdensity should have made it one of the first galaxies ever identified. Instead, the dense dust of the galactic plane masked its signature. Large-scale surveys smoothed its features into the background. Even when early hints appeared, they were dismissed as irregularities in the Milky Way structure. Only when infrared and near-infrared maps penetrated the dust did the dwarf's presence stand out. This underscores a fundamental challenge in the cosmic census. If a galaxy can remain hidden a mere tens of thousands of light-years away, how many more escape detection at vastly greater distances? Dwarfs are particularly vulnerable to invisibility. They are faint, diffuse, easily disrupted, and often lie behind brighter foreground structures. Across the universe, countless dwarfs likely remain unseen because they are masked by denser regions, overshadowed by bright companions, or blurred beyond detection by dust and distance. Even classification becomes ambiguous when a galaxy is deep inside the process of being cannibalized. Is the buried companion still a distinct galaxy, or is it now simply a stellar stream? At what point does emerging satellites cease to exist as an independent entity? These questions complicate attempts to define what counts as a galaxy. A system like this challenges the very definition existing both as a distinct dwarf and as a dissolving part of the Milky Way. Surveys, especially deep sky counts, must make judgment calls leading to inconsistencies in how similar systems are tallied across different catalogues. As we drift away from this hidden dwarf in our imagination, its features blur quickly. The distinction between Milky Way stars and its debris fades. The tidal streams dissolve into the background halo. Eventually, the dwarf itself becomes indistinguishable from the Milky Way it is merging into a ghost swallowed by a giant. Only with specialized observations could anyone ever guess it was there. This quietly dissolving companion teaches us that galaxies can hide not only across cosmic distances, but even within the boundaries of larger systems. It warns us that the galaxy count is incomplete, not only because the universe is vast, but because some galaxies are simply lost inside others, erased by time dust and the relentless pull of gravity. When astronomers first pointed a major telescope toward what seemed like an empty patch of sky, no bright stars, no nebulae, nothing but darkness, they expected to find very little. But what emerged from that darkness changed our understanding of the universe forever. In the Hubble Deep Field and later in the even more revealing Hubble Ultra Deep Field, thousands of galaxies appeared where nothing had been visible before. Not a handful, not a trace. Thousands, each one a distant island of stars, some so faint that only days-long exposures could capture them. It felt as though the universe had chosen to reveal a secret hidden behind the surface of the night sky. Yet these deep views carry another more subtle lesson. The farther we look, the fewer galaxies we seem to detect. This is not because the universe runs out of them. Rather, it is because distance strips galaxies of their ability to be seen. Light weakens, details dissolve, structures shrink beyond recognition. Even the brightest systems from the earliest epochs now appear as tiny smudges so small that a single pixel may hold an entire galaxy. The deep fields do not show us the full population. They show us only the galaxies that survive the brutal thinning caused by distance dust and cosmic expansion. In the deepest regions of the sky, many galaxies are barely visible at all. Their light has stretched into longer wavelengths, reddened by billions of years of expansion. What began as ultraviolet or blue starlight arrives at Earth as faint infrared signatures. Some galaxies radiate so softly that even modern telescopes fail to distinguish them from background noise. Their structure dissolves into the static, leaving behind only hints of what they once were. In these fading silhouettes, we witness the unavoidable truth. The universe becomes more invisible the farther we look. When the James Webb Space Telescope opened its golden mirrors and peered even deeper, it found galaxies farther back in time than any previous instrument. Tiny red dots representing systems that existed just a few 100 million years after the Big Bang. Many of them are so compact that they can barely be resolved, their shapes blurred by distance and by the limits of our optical tools. The earliest galaxies are small, chaotic, and intensely active, but from our vantage point they appear as little more than sparks flickering at the threshold of visibility. Even with Webb's sensitivity, countless more remain hidden in darkness. Deep fields reveal another complication. Surveys are biased towards certain types of galaxies. Bright young star-forming systems stand out easily, while older, redder, more diffuse galaxies fade into obscurity. Ultra-diffuse giants, despite their enormous sizes, vanish completely at great distances because their light spreads too thin. Dusty galaxies glow in the infrared but are invisible in optical images. Galaxies rich in heavy elements appear dimmer than their pristine cousins in the early universe. Every wavelength, every exposure time, every camera creates its own version of the cosmic census, each one incomplete in its own way. This means that even the deepest images humanity has captured are only partial snapshots of the universe. They show us what rises above the threshold of detection, not what truly exists. The deep fields are windows, narrow openings through which only the brightest and most persistent galaxies pass. For every one we see, many others remain erased by distance or disguised by faintness. Imagine trying to count mountains across a foggy landscape. The tallest peaks stand clearly above the mist, but the valleys and smaller ridges remain hidden. That is what deep fields show us. The peaks, not the full terrain. The deeper we look, the more the universe stretches into abstraction. Galaxies lose their spiral arms. Their cores blur. Their clumps of star formation collapse into soft glows indistinguishable from one another. At extreme distances, we cannot even tell if a faint drop of light is a galaxy, a star cluster, or a distorted echo caused by gravitational lensing. In some images, entire populations of galaxies appear only because the gravity of closer clusters magnifies them like a cosmic lens. Without that magnification, they would vanish entirely. This gradual fading tells us something profound. The universe is not sparse at great distances, it is simply hidden. The farther we reach, the more galaxies slip beneath the surface of visibility. Even with the best tools we possess, we are only scratching the faintest layer of an incomprehensibly vast population. The true number of galaxies cannot be derived from what we see in the deep fields. It must be inferred from what we know we cannot see. As we drift away from the ultra-deep field in our imagination, the thousands of galaxies shrink into a small luminous patch. Step back farther and they merge into a single glow. Move farther still and that glow fades completely. The universe's richest windows collapse into a speck of light, and then into nothing. Not because the galaxies vanish, but because our eyes and instruments cannot reach them. The deep fields teach us humility. They show us that what we perceive as emptiness is often a consequence of our limitations, not the universe's. They reveal a cosmos overflowing with galaxies far more numerous than any image can contain, and they prepare us for the final realization of this journey, that beyond even the deepest views, beyond the faintest smudges and reddest horizons, the universe continues filled with galaxies that no telescope will ever see. Even the deepest images, the ultra-deep field, the earliest galaxies seen by Webb, do not show the universe as it truly is. They show only the part that light has had time to reach us from. Everything else lies beyond our cosmic horizon, a boundary not made of matter but of time itself. The observable universe is not a physical edge. It is the maximum distance light can travel since the Big Bang. Anything farther away is still there, still expanding, still forming stars, but forever hidden behind the speed limit imposed by the cosmos. This horizon grows with time. Every second that passes, more of the universe becomes visible. Yet the expansion of space pushes distant galaxies away faster than their light can compensate. Beyond a certain distance, about 46 billion light-years today, galaxies recede so quickly that their light will never reach us, not even if we wait for trillions of years. This means the universe extends far beyond what any telescope can observe, perhaps infinitely. And whatever lies past that horizon contains galaxies as real and numerous as the ones we see, only unreachable. This disconnect creates a strange paradox. The universe is full of galaxies, yet most of them are forever inaccessible. We can infer their existence from model simulations and the uniformity of cosmic structure, but we will never see them directly. They are stitched into the fabric of the cosmos, entangled in the same large-scale web of dark matter arranged in filaments and clusters, but they exist outside our visual domain. This is not a technological limitation. It is a fundamental boundary written into the physics of space-time. Even more unsettling is the fate of the galaxies we can see today. Because the universe is accelerating, many galaxies presently visible in deep fields will eventually drift beyond our horizon. Their light will stop reaching us. One by one, they will dim, redden, and disappear into the cosmic night. In the extremely distant future, only the local group, the Milky Way Andromeda, and their satellites will remain visible. Everything else, from majestic spirals to ancient ellipticals, will fade into an unreachable void. The night sky will grow emptier, not because the universe contains fewer galaxies, but because expansion hides them. This realization transforms the question of how many galaxies exist into something far more profound. The observable universe contains at least hundreds of billions of galaxies, likely trillions, but the total universe may contain numbers vastly larger. Some estimates suggest that the entire cosmos far beyond our horizon could hold galaxies numbering into the quadrillions or more. We cannot know. The light from those distant realms will never reach us. They exist in a cosmic silence beyond even the reach of imagination. Yet their existence shapes the universe we can observe. The distribution of matter, the patterns of cosmic microwave background radiation, and the scale of large structures all point toward a universe much larger than the region we inhabit. The cosmos does not end at our horizon. It extends outward like an ocean whose far shores we will never see, and in that ocean lie galaxies without number, structures that formed, evolved and faded without ever sending a single photon in our direction. As we drift outward in our mind's eye approaching the boundary of the observable universe, the galaxies grow fainter and redder until they vanish entirely. Beyond that lies a darkness filled not with emptiness but with everything we will never see. And in that hidden vastness lies the clearest answer yet. The universe contains far more galaxies than any human will ever count. Throughout this journey we have visited spirals, dwarfs, starburst furnaces, faint giants, tidal wrecks and galaxies so diffuse they almost cease to exist. Each one revealed a flaw in the idea that galaxies can be counted like items on a shelf. The universe is not organized. It is dynamic, merging, dissolving, fragmenting, and creating new structures at every scale. A galaxy is not a fixed entity. It is a process, a phase, a snapshot of something that will look very different in another billion years. Mergers blur boundaries. Two spirals become one elliptical. A dwarf nearing its end becomes a stream. A tidal tail holds clusters that may grow into new dwarfs. How do we count such transformations? When is a galaxy finished? When does it stop being one? The universe refuses to draw clean lines. Brightness creates biases. Galaxies with active star formation look large and brilliant, tricking surveys into overestimating their mass. Ultra-diffuse galaxies, some larger than the Milky Way, vanish because their light spreads too thin. Dusty starbursts shine in infrared but disappear in optical surveys. High metallicity galaxies may appear dimmer than pristine ones, skewing early universe statistics. Resolution adds error. A merging pair becomes two galaxies in one survey and one in another. A faint cluster of star-forming knots may be misclassified as a single compact galaxy, or as multiple dwarfs. Orientation affects what we see. Edge-on spirals become thin lines, while face-on spirals reveal grand arms. Tilt them slightly and classification breaks. Time distorts perception. Light from distant galaxies shows them as they were billions of years ago. We see early dwarfs that have long since merged. We see ancient ellipticals at their prime. We see spirals before they were disrupted. The galaxies we observe across cosmic time are not contemporaries. They are a mosaic of epochs layered on top of one another, and beyond all biases lies the ultimate limitation. We only see galaxies bright enough to reach us. The faint majority remain invisible. For every galaxy in the deep fields, many more fall below the threshold of detection. Some are too distant, some too diffuse, some too obscured by dust, some too small, some simply too unlucky to lie in the narrow windows our telescopes target. All these layers combine into an inescapable truth. Any number we propose is an approximation shaped more by what we cannot see than by what we can. And yet this is not a failure, because the purpose of counting galaxies is not to reach a final tally. It is to understand the structure of the universe and our place within it. The diversity of galaxies reveals the forces that shape them. Gravity, dark matter, feedback mergers, cosmic expansion. The difficulty of counting them reveals the scale of the cosmos and the limits of our perception. The impossibility of the task is the point. It reminds us that the universe is richer than our senses, larger than our tools, and more complex than our classifications. It humbles us, it challenges us, it inspires us, and it prepares us for the final realization that the true value of this journey does not lie in a number but in the wonder stirred by trying to find it. Imagine leaving behind every galaxy we have visited. Giants, dwarfs, spirals, rings, collisions, ghosts of dark matter and drifting back toward the Milky Way. The light of each system fades one by one until all that remains is the soft glow of our own spiral home. Beyond the dust lanes of the disk, beyond the halo of scattered stars, lies the quiet region we occupy. A small blue world circling an ordinary star in an unremarkable arm of a galaxy among trillions. The question that began this journey, how many galaxies exist, now feels transformed. It is no longer a question about quantity but about perspective. The universe is so vast that even our largest telescopes reveal only a thin slice. Beyond that slice lies a frontier we can never reach, filled with galaxies that will never send their light our way. Yet their existence is certain, woven into the cosmic web that surrounds us. Trying to count galaxies is an act of curiosity, not precision. It is a declaration that we want to understand our place in a universe far larger than ourselves. It is a reminder that knowledge expands only when someone dares to look into the dark and ask what lies beyond. And so the final answer is this: the number of galaxies in the universe is not fixed. It is not knowable. It is not even meaningful in the ordinary sense. What matters is that the universe is overflowing with them far more than we can see, more than we can imagine, more than we will ever finish discovering. As we return to Earth in our mind, the night sky regains its familiar form. The constellations settle back into place. The Milky Way stretches across the darkness like a pale river of light. But now something is different. We know that behind every point of darkness may hide a galaxy. Behind every faint smudge may lie an entire world. Behind every deep field lies a universe far larger than any map can capture. The journey has not given us a number, it has given us something greater. The understanding that the universe is vast enough to remain forever mysterious, yet close enough for us to explore with wonder. And in that balance between the known and the unknowable lies the beauty of astronomy, the joy of asking questions whose answers forever expand the horizon of what it means to be human.